Who is the is it over here? No, but there's already one host. I cannot close your mic. Yes, yeah.
Yeah. Now. You don't.
No. Yeah, it was.
It was you.
Yeah.
Okay. Hello, everyone. Do you hear me, people online? Please, if one of you can talk.
Yes, we can hear you, Matthew.
Can hear you.
Thank you. Welcome, everyone. Perfect. Okay, so perfect. We can start this afternoon. Just an introductory speech, very brief. Welcome, everyone, and for people who join us this just after lunch. Very delighted to greet you and welcome all of you this afternoon for the first session of the Capstone Project Defenses of the first edition of the Master. We are very, very happy to have finally this climax of the project. We start today with French companies, and right away with Altametris, then Eurobios, then Siemens Gamesa. So we have people online, and some students and some partners and some supervisors, and a lot of the students mainly here. I take advantage to thank all of you, obviously, and all the partners, supervisors, for all your works. It has meant a lot for us. So how do we proceed? We have 3 presentations. Each will be the same, 45 minutes maximum of speech, of a lecture, and then 50 minutes of question and answer from the jury. Regarding the jury, only known faces. We have Thomas from BME, Thomas Robas. Alexandro from UPM. Christian Trenka from UPB. Birgul from ITU, as you know, and Jeremy from ENPC. So we'll start with Altametris. And just before starting to defend the project, I just wanted to give the floor to Guillaume Villemin, as a representative of Altametris, because Altametris is a partner of the consortium of the project Digital Twin. So Guillaume, thank you for coming. And you have the floor for few words.
See you there.
You can come here, come in the middle.
Thank you, Mathieu, for giving me the opportunity to present Telemetries. And well, we're a subsidiary of SNCF Réseau, you know, the French railway infrastructure manager, and being part of this as a partner of this master is a great opportunity for us to be in touch with academics that work on that topic, and be able also to be in touch with skilled professionals that want to be even more skilled in that topic of digital twin. And we were really happy to give. now I'm recording. And yeah, we are very glad to be able to give a subject for this Capstone project, as digital twin is a real subject for asset manager and railway infrastructure in general. So I hope you enjoyed the presentation of this results of the project of the great group we had on that topic. And I won't spoil any of the conclusion and the work, because they will present it very well.
Thank you, Guillaume. Just for the audience, we have also Anis Charalak with us, who was a supervisor, and also Nicolas Audebert.
We are presenting.
Okay. Just to say that they are in the audience.
Just for you to know, guys, I will. How do I take out this?
You have to move it. Yeah, that's it.
But I cannot.
It will get. I think it will. If you don't click on it, it will disappear. I think. You can try like. If you don't, yeah, maybe at some point.
All right. You're set then? Yeah.
Yeah, you can start.
So,
No.
and you guys, they are so you guys talk about the usage. Okay. Okay, so
Internet y se ha quedado se ha desconectado internet y se ha quedado pillado en la retransmisión.
no,
¿Cómo se hace? Pues si vuelvo a pasar.
For us, we will introduce ourselves later, no?
Ya lo he retomado,
No, it doesn't work
Sí,
now.
por moverme.
There you go. Of the presentation, introduction of the subject, then the objectives that we set for the Capstone project. We are then going to jump onto the methodology and all the planning of our work. Then we are going to be talking about the development of the project itself during the last 6 months, no? And then some of our conclusions on the results, no, and the next steps. If you can pass, no, the other way. So regarding the team, well, myself, I'm here. That they cannot hear me.
Yeah.
I don't speak slow.
I know. Probably it's kind of probably the.
Is now better? I don't see them. So.
The problem with the laptop, you have to speak to the laptop.
No, it's not the laptop. The microphone.
Oh, okay.
Can you hear us now?
Yes, we can hear Victor, but when some people are talking in the audience, we stop listening to hearing what he's saying. So that's the problem. But now we're hearing him perfect.
Thank you, Luis. So I'm Victor Aparici. I am a BIM manager at IDOM. I am on the railway sector as well. So that's why this Capstone was really interesting to me. No, and well, my colleagues are Fuad. If you want to introduce yourself.
Fuad Arag, I am technical responsible at FH company, and I work in the domain of bridge domain and also BIM management.
Judith?
Hello, my name is George House. I'm from SEA company from Hungary. I'm an architect and also BIM manager.
Hello, my name is Beatriz Crespo Martin. I am the digital leader in the transport business line at Capstone. My role involves developing digital strategies that support the business and expand the services offered by the company. I am grateful to have had the opportunity to complete this executive master, which has enabled me to consolidate my expertise, extend my digital capabilities, build a network of professionals with whom we can continue to share our knowledge. So thank you very much to our professors and tutors, academic supervisor, Nicola. Muchas gracias. Thank you very much. And our company supervisors, Anis and Levi, and of course, Guillaume of Altametrics.
So regarding the subject, well, scan to beam, basically what refers to is the methodology or process of capturing the reality, no, and being able to model existing assets. No, the scan part comes from the laser scanning, which will produce point clouds, no, which are clouds of thousands or millions of points in some cases. And then the beam part obviously comes on the identifying the elements or the objects that we have in those point clouds and developing a model out of them. Obviously, this process right now is a manual process. So actually a modeler has to be identifying the objects and then placing the right elements where they are located, no? And the aim of the project was basically to try to automate this process within the railway sector, no? But in this case, in some other sectors, this has been going on for some time now, no? And obviously, what we wanted to know, no, Judy, is how was the state of the art in this subject, no? Do you want to tell us?
Okay, thank you. So let's speak about a little bit about this scan to beam solution. So I don't know how many of you ever was part of some scan to beam project in their own company, but in the professional life and professional use of point cloud modeling, normally it takes in consume a lot of time in human resources. Currently, this is the current technical level, but with the development of automation and data processing, and even the AI research, we can say that this kind of procedures and processes for the companies became more fluid, and you will be able to meet the shorter deadlines or reflect back to the market needs or the requirements in a shorter period of time. If you'll be able to implement this kind of solution into your daily routines, for example, on the scan to beam project. So the impact of the AI in data processing. So first of all, from a point cloud, you need to remodel something according to the point cloud survey. But first, you need to extract the data from the point cloud somehow. So normally, it can be made by manually, but with the AI, you can research or develop a new process which identify the object more easily, more precisely, so you can improve and develop the precise model generation, and you can automate it with this parametric programming. So next one, okay. So with Altimetrics, after we gather insight into a family repository and unclassified and also classified cloud survey, we were able to create 4 scenarios for this project. this Capstone project, as you can see on the picture. In the first option, it was discussed that from a classified point cloud, we got the parameters. It was generated manually or by some machine learning process aided by Altimetries, and we only do the modeling phase and visualization and a few software. The second scenario is a little bit different because in a classified point cloud, we develop, the students develop the parameter in a data extraction. And after it, we create the model and the visualization solution. The third scenario, we not only use the point cloud, but the orthophoto. Thank you, the orthophoto as well. So from the orthophoto, we could identify the objects such as electrical cabinets or some other part of the line infrastructure and the railway. And from the point cloud, we would be able to get the location, the XYZ, the coordinates, everything else. And then we were able to model it and develop that and visualize it in a separate way with the IFC aided model data transformation. The scenario 4 was the most complex when we used this classified point cloud for further segmentation, which made possible to develop further object recognition and pattern analyzation to extract the parameters in the data in the point cloud. And after it, and in the other scenarios, we also use the modeling phase and the visualization. So the chosen one was the second scenario. It was discovered with Altimetries during this 6-month period. Before the development, this was our first bigger milestone, and we can say it. And okay, so this approach would be a first or good. So this kind of research aims to a bridge to get between the manual processes in the fully automated work. So next one, please. Okay, and about some so the challenges. First, so we are in a digital transformation era in the sectors, in the AEC company as well. So which means a greater burden on the company's shoulder to adopt this new kind of digitalization evolution. And this means normally slower processes and time-consuming workflows. And also, we can talk about the digitalization of assets, where the asset managers and all the public administration can meet or face all of the same issues during their works, how to digitize their assets and their model elements. So here comes the scan-to-bin automatization, which is a key role for this kind of development, where the railway sectors in every kind of line infrastructure can be the ideal sectors or segments of the industry where we can start this development, because it's not that complex geometry you can get from the point cloud story.
if I would have to compare, for example, a building point cloud service much more complicated in the geometry. Through the automation of data, to model or digitize your assets or geometry, it's very important also how to extract the data in the point cloud and how to process this data into the modeling phase to help speed up the digitization process itself. And there are the other sectors of the industry with more complicated geometry, which is also further in the detailed developments in the requirements. So because so this kind of scan to beam processes will spread all over in the industry, such as for the ports or energy grids or the roads. This can be done. Next one, please.
Yes, and now Fuad, I think, is going to jump onto the objectives. Step forward, if you
For the main objectives, after reviewing all documentation and potential scenario, the main objective of the project is to develop a workflow that automates the creation of beam model for a railway infrastructure. This will involve automatically extraction object information, such as array and catenary pole, from a point cloud and visualizing it through a web application. The initial focus will be on the category as foolproof for a concept of the workflow. The objective is divided. Our objective is divided into 3 key steps, which correspond to the workflow. The first step is extraction. The second is the model beam creation. And the third one is the visualization. These objectives outline a plan of automate what is typically a manual and the time-consuming process, aiming to enhance efficiency and accuracy in infrastructure project. For technical objectives, in order to go far from the main objective, from previous objective, further decomposition can be made into technical objective for each phase of the workflow to create a more comprehensive task to be developed. For the first step, we developed a point cloud loading and breakdown analysis of each element in the cloud point, how to identify object and extract information from the cloud point. For the second step, for the beam modeling, how can we create a CAD library, beam CAD library, by modelizing Revit families of the category. The second step, using how to use Dynamo in order to automate the placing of this. First, how to identify this family category, family type, and place it in the global project. For the third step, the visualization, we start by benchmarking all application viewer in the market, definition of the requirements of the viewer, a viewer choice according for research, and at the end, a viewer developing a viewer for the application. For methodology, as I said, we have 3 main steps. The objective of the workflow is not just to develop the 3 main steps. We include between each step, between extraction and the modeling, between modeling and visualization, a validation step, in order to be sure that the extracted data is well extracted, the accuracy of the beam model generated is well done, and the visualization to validate the visualization also.
So we are explaining all the parts of the methodology. The extraction process includes the workflow from the initial data provided by Altametris, which consists of classified point clouds. to obtaining the parameters necessary for the tracing and sizing of each individual instance of the quaternary force. The process includes 4 steps to complete the methodology. 1. Point cloud loading and breakdown. The point clouds provided by Altimetris were already pre-processed and contain a classification scalar file field that can be used to identify the different parts of the point cloud through various classes defined within it. At this stage, individual elements will be filtered to study them separately. Second, analysis of individual elements. It will then be necessary to select the most common, standardized, and repetitive elements as the basis for the study. Once the elements have been separated and selected, the next step is to calculate the different simple point cloud data in order to ascertain what information could be extracted and which parameters will be most helpful in identifying the type of quaternary. The third step, parameter identification and data extraction. At this point, additional mathematical methods are used to evaluate data and determine the parameters. And the last one, data validation. The information is validated through calculations and another extraction algorithm is applied using Rhino and Grasshopper to ensure the accuracy of the data from the point clouds.
For the BIM modeling part, the breakdown was on BIM modeling, automation with Dynamo, and of course, as Fuad said, model validation. For modeling families, as you know, quaternary posts are quite a standardized element. So we decided to use the tool Revit from Autodesk because of their possibilities with families. We could develop standard families for different type of quaternary posts, and then we could use them or change them from the family if any change was needed within the family itself. Then we jumped onto the automation. So, okay, we've done the standard families, but we have to place them now. So from the extraction part that Bea mentioned, we have parameters extracted into the CSV. So what we use is Dynamo, which is a tool within Revit for visual automation. We were able to develop the code for placing these elements in the right place with the right orientation and so on. And then model validation, of course. So what it was again Rhino Grasshopper, which is a parallel method of doing the same exercise in order to be able to validate that what we were obtaining in Revit was the same as we could obtain with other softwares. This helped us on comparing the results and being clear that the path that we were taking was ready for the next step. And then on the visualization, Judy is going to jump on that.
Thank you. So visualization consists of several processes. First, we had to do a research. So because we would like to check the academic approach also and check what's on the market currently as a possible software solution. Then with Altimetris, we define a functional and technical requirements and extract the key requirement to establish a minimum viable product from which we could develop the complete viewer itself. So after this requirement definition, we created 3 scenarios for the development. So first, what if we use a freeware, for example, or what if we use a software from the market, but it always was complicated because of the licenses, and one of the requirements was to be a freeware software, must be a freeware software. in the end of the development. Yes, the third scenario was this open source solution. So what if there is a root program on the internet and you can develop for yourself with some pre-made modules. So the viewer development after this minimum viable product was determined. We have to develop and deploy this solution into phases. So with minimal functional deployment in the baseline development with essential technical deployment. In the end, here we also have this validation process for this viewer visualization solution according to the minimum viable product requirements, and in the end, we deploy the full development. If we jump to the next session. Yes. And here is our scheduled timetable for the last 6 months. How we did this Capstone project development first. As we mentioned, there was a point cloud loading and breakdown how to what kind of point cloud we have. So there was an unclassified and classified point cloud survey. Finally, we used a classified point cloud survey because it was easier to identify the elements and extract the data in the end. So we use the cloud compare free software for this one. Parallelly, the viewer and visualization research has started. And then we had several meetings with alternatives to discuss the requirements and also to find the best solution for the viewer and choose a scenario how to develop in the further. But also parallelly the parametric validation has started in Rhino and Grasshoppers before the final version in Dynamo was created. In the middle of April, after the analysis of this RFA and IFC repository, we successfully found a quaternary pole family, which was the basic of the further family development. It was revealed from the point cloud survey that there is a very different quaternary pole type, which was not in the previously created family repository. So we have to build up almost from the zero, but partly we were able to use developed parts.
Yeah, so the key part here, yeah, is like, so we basically decided to put together the 3 lines of production at the same time because of the very tight deadlines that we had. No, so we started working in the extraction, but as well in the viewer part. No? And then diving into the details. So we get into the extraction now. So I'll go into a bit more technical now, but we have mentioned a few times that Altimetry was providing classified information. So classified point clouds. So this was key. They already come with developed methods for classifying point clouds. What does that mean? This means basically on being able to identify the different groups of points, no, and the different parts that they are part of, no. So they counted with a methodology that already classified different elements of the point cloud, such as rails, catenaries, etc. So we decided to focus on catenaries because they were quite a singular element. No, for that we have used, as you can see, Cloud Compare here is a free solution for managing point clouds. You could see that from the raw point cloud that we have, we already have a classified point cloud where we can identify the different elements. We use the Python version of Cloud Compare. These allowed us to automate. So the duality between them helped us on developing the workflow within Cloud Compare and then automating it by with Cloud Compile. And then for that, obviously, we use Python with Jupyter notebooks. And as we mentioned already, we extracted that into CSV for the use on other software. So, and validation, of course, came with Rhino Grasshopper, which is also a really powerful tool because it can interact with point clouds as what we'll explain later. So if we jump onto the specific process, so as I said, we had the process of loading the point clouds into Cloud Compile. We didn't have any issues on size and so on. I think we even with normal computers, we could easily use or manage a normal point cloud. Then we had to identify the scalar field where the catenary poles were located. This is easy because the classification always is standardized, so we will find them, the catenary post, always in the same layer, let's say. No, for that, we had to filter that classification, and we will have a point cloud of all the catenary elements. No, and then obviously, because we will still have all the points together, what we need then is to being able to split this point cloud and being able to identify, as you can see here, the catenary elements by itself. No, so identifying all the point clouds that would belong to one single catenary post. In this process, the key part, Cloud Compile counted already with function that could help us on splitting the point clouds. But obviously in here, the key was on being able to get the right parameters in order to for the catenaries to be split correctly. Now, if we filter too much, we could divide in half a portal, no, which will have two posts. Or if we were not precise enough, then two confronting catenaries could be considered as one. So we had to be very precise on the division there. Yep. And then once we had the single catenary post, what we did was other mathematical calculations. So we identified, for example, center of mass of the catenary, no, in comparison to the center of geometry. So that would give us a clue, for example, on the type of catenary that we had there. So, for example, on the portals in the plan view, we will have the center of geometry and center of gravity almost at the same location. But as you can see here, because of the cantilever that they have, no, the center of mass will always be located closer to the post location. And then also other mathematical methods such as regression lines could help us on identifying axes within plan view or vertical view. No. Then up to here, what it came, it was the process of defining clearly the different parameters. No. And if we jump onto the next slide, the key here was identifying what were we going to extract, or which information we were going to take out of the point cloud in order to be able to identify and then position the catenary posts. We simplified this at the beginning and then started adding value to it. But basically what we did, it was in order to identify the section of the post, for example, what we did was divide the point cloud in half. So we will always have the bottom section, which will identify perfectly the section of the post. The section of the post will help us on identifying, for example, X and Y coordinates, no, which will give us the center of gravity of that section will give us the center of the location of the post. And then obviously what we needed was to know or understand the rotation angle. For the rotation angle, as you have seen before, we use the regression line of the plan view, and that helped us on orienting the point cloud and being able to rotate the elements with that precise angle, no? And of course, as the last step of each of our capstone phases was the data validation, which Fuad will explain.
Yes, as an output of the extraction phase, I receive a CSV file, but it was very difficult for us to validate the information. That's why we proceed with a parallel process using another software, which is Rhino and Grasshopper. Grasshopper is the equivalent of Dynamo for the Revit user. And we start exactly the same job that done by the Python language or Cloud Compile. We start from the global project or from the last file, the classified last file that Altimetris gave us. We start to split the model, isolate each category itself, and try by step taking the mean point, the mean xy of the point, the max ui point, generating the axis of the point, and at the end we extract the rotation of the catenary. At the end we extract the coordinate of the catenary, the height of the catenary support, the top and the bottom arm length, the orientation of the catenary. And with this information, with these two information, it gave us the possibility to compare the result and to validate this step.
Then, Julie, are you going to jump on the modeling part?
So before the parametric beam modeling, we have to prepare the families in Revit to be able to overdrive it with Dynamo. So after the analysis of the given repository, we found a total table family, a category family, and we kept the original structure in type. So we prepared a generic type family for modeling, and we also kept the nested family solution, which means I was able to embed not one but several other family into one family, which help us to put the parameters in every family, which was readable, and we can manipulate it with Dynamo in the end. So it's a loadable family. It's very important. It's not a system family, it's a loadable family, not an in-place family, because the in-place family is unable to give later another specific parameter of the loadable family. You can do almost anything. And to insert this family according to the given coordinates extracted from the pointer, you need to use adaptive family, which means the family in the base point of the catenary post was inserted with adaptive points. It was the leading point of the family where it was inserted in the model space. And we added the rotation parameters, which also can be overdriven in Dynamo. And according to the extracted axes of the catenary posts and the degrees from the axes of the catenary, it will be able to give the real space rotation of the elements. And also, because we works with the vert coordinates, so the height and the x and y coordinates was represented in the vert coordinates. We had to prepare the software to use this kind of solution and to change the values into normal model space value for the family. Just from the height from 0, the pole height, the lower arm and the upper arm length, and height as well, and also the whole family rotation from the x-axis. And the result, we created three family, two single type catenary and one portrait type. It also came from the point cloud, and it was more simple than the original one because the recipe level was only meant only 4 families, not 5. And as you can see here, this is the ordering. So the yellow was the first level, the red was second, and the green as well. And here is the rotation. The rotation parameters was created by a simple reference line solution. It was bind together with the elements in the model space. We talk about beam modeling. We also have to talk about the LOD and the LOI for the family according to the ISO 19663. But as we kept also the 300 level of details because it was the original one, and we have to create only the precise geometry in the model space without any extra level of information. We can consider that. Oh, yes. And finally, we have to make the parameters with extracted data that you can see in the line. We got the XY coordinates in a CSV file, and we matched to this named parameter line in the family, and also for the elevation and the category, the height parameter, rotation, etc. And with this kind of parameterized modeling, we were able to manipulate and override the default values in the family parameters. We have to put the model together.
For the automation part, I use the Dynamo in order to develop a script. For the first step was to import cloud points into Revit. It was very difficult because Revit don't accept the last file. For that, we use the recap in order to convert the last file to RCS and RCP file. And after that, we upload the cloud point in Revit. The second problem that we have that Revit don't accept very far coordination of point. For that, we create a point-based project, and we jump to the Dynamo. In this step, I have just to do the link between the extracted data as CSV file and parameters that are existing and developing by Yuri in the CAD library. The main objective of this part is reading the data from CSV file, preparing it in order to be as the organization of the parameter in the family type. The main difficulty was how to identify exactly the family type that is developed in the CAD library, how to call it in order to use it in the model. For that, we developed some Python script based on parameters. If height of the category is up to 8 meters, it will be tilt type, and like this in this way. For that, we develop script that use the coordinate of XYZ of the support of the catenary in order to place it. For the alignment exactly, I use the rotation value that Victor extract from the point cloud and inject it in the family in the family parameter. And the result, we see that we have generated all family catenary family type in the model global. For the validation, for the visual results, we were very pleased to see the model placed in the cloud point, but it wasn't sufficient. We were waiting for how to can measure, how to can exactly validate the model and tell by precision how was the precision of the model. That's why we were thinking about how to use cloud compare or recap in order to generate the catenary mesh and do the comparison via machine learning or other programs in order to compare the difference between the two models. And we were thinking also in the future, maybe how to train a model in order to do this job. But for the moment, the result is we developed something really that can we appreciate.
So the last step it was visualization, and the main purpose of the last part of visualization is to provide an online viewer application that allows quick and effective consultation of the model created from the point cloud and automated way. To arrive at this solution, research and conducted to identify the solutions that were available on the market and in the academic field that could be used to solve the visualization of BIM models from an open source approach. After careful consideration, we have decided to select our own open source solution, which is scalable and adaptable to the minimum requirements needed to complete this phase. This is the sequence to develop and deploy the visualization solution. One input. Okay, one input.
No.
Stay. One input. We have the IC model resulting from the export of the native model obtained from the previous stage. Then we have the process, that means cooking the solution from Node.js and the open source code offered by that open company as a managed solution from Azure DevOps. And then the output, online viewer hosted in the cloud to consult AFC models in compliance with Altimetry's requirements. Next, please. Right now, once the Altimetry's, no, wait. Once the Altimetry's requirements for this phase has been gathered, the viewer was developed in 2 stages. The first step was to create a minimal viable product that will allow us to test the minimum functionalities of the viewer, namely the loading of BIM models and the potential federation of them in the same session. The video right now demonstrates the straightforward process of loading a model. You can see it's going to be the Capstone. And then there are a minimal button, please, here, that you can load the ISFC model. Here you are. This is the minimal expression of a viewer. Next, please. Once, while the one on the, then the other part of the minimal viable product illustrates how models can be federated by adding IFC words in the same session. Please. In the same session, you can load one discipline, like I think it was architecture, I don't remember. Let's see. Come on. Here you are. And then we are adding the different disciplines in the MVP project, in the MVP viewer. This is the next step of the minimal expression of a viewer. But we don't stop here. We continue to develop this solution. In the next slide, please. So, upon the initial step was complete, our team proceeded to develop a comprehensive solution, integrating all the essential functionalities required to consume IFC models in an online viewer. Below here, we are going to see a series of videos that demonstrate each of these functionalities, as this first one that shows us the visualization control. Please, play. Here you can orbit, zoom, and punch. And then you can have an extend view. And then you can freeze the view, and then you use the mouse, and you can move it, can't move it. And then you can select the objects and disappear, or put in the screen and isolate it. This slide shows how to federate model, and the next one, how to consult them in the browser. For the federation, and contrary at the first MVP, we can consult the loaded models in the left panel. Okay, please. Then in the left panel, the first one is federation. Okay, thank you. Here you can consult the loaded models, all the different models, catenary, architecture, wherever, and you can play and display the visualization. With this functionality, we can control the display of the loaded discipline, consult the entities of each IFSC model, as you can see, and select them on the panel to display them on the model. Here you are. Next, please. And finally, consult the properties of the elements of the model. So you can select one object and then consult all the attributes of this object and even the property sets in the IFC. To conclude and validate the viewer, we have compared the requirements covered by each of these developments. As you can see, in some cases, we have added requirements that were not requested by Altametris, but we consider it important for each activity, such as the visualization of several models at the same time on the MVP. That means here you are, the MVP requirements. This is Altametris request, and this is our development in the viewer. And this is display of several models simultaneously, federate models, and they don't specifically require it, but we are developing this. And in the complete development model viewer, this one, we have added the functionalities to control the visualization of the model, orbit, pan, freeze the view, but we add the navigator of the models and the complete consultation of the elements, not only their geometry, but also of the data contained in their attributes. For example, all this package, minimal option consult the elements, not only the geometry data. So this is our process, and the results are.
Yep. So for those that are still with us, just give me 2 more minutes and I'll close the presentation. So results. The first one, have we achieved what we were looking for? I think yes, we did. We succeeded. No,
Yes.
we managed to develop something that automated the process, although there's still work to do. The second one, most important for me at least, no, is did we learn something? Yes, we have learned something. I think we have improved our programming skills. We were all from the BIM side of things, so we obviously focused on that part, but we jumped onto viewers, programming in Python and so on. So that was really interesting for all of us. And then limitations that we found along the way. Well, that one as well. No, so we didn't have probably the best skills, but the master definitely helped us on developing them and being able to come to a successful end of the project. And I think that's more or less what we wanted to say regarding specifically the Capstone project. Regarding further conclusions, so you would say, okay, you've talked about the scan to BIM, you've talked about the point clouds, but how this relates back to digital twins. Well, for us, I think we found that this is a key part of the digital twin development, and you would say why? Because, for example, in sectors such as the railway sector, the most challenging part that they have is being able to digitize the huge amount of information that they already have in place, no, existing assets. So with this sort of production, we can make the scan to BIM a commodity, no, something that will be done automatically, and that the railway companies would be able to review their assets, scan them twice a year, and being able to compare both situations, no. And we've done or focused only on the catenary elements, but there's, I mean, the simple process that we've done can be moved into other things like cabinets and so on, which are still punctual elements. And then it also set up a base for other type of elements, such as linear elements, to be done as well. And obviously what we've done in the railway sector can easily be reused in the road sector, which they have the same typical elements, which are linear elements and punctual elements. So we believe that this sort of like proof of concept that we've done will help will help the companies and understand the potential of these type of methodologies, no? And with that said, what I wanted is well, to thank you all for staying with us for this almost hour. And obviously, thanks to Altametris for their information, for their support, also to Nicola. And well, thanks to the team as well for being able to develop all of this. Thank you.
Thank you all for your lecture, and it's time for an exchange with the jury. So who wants to shoot first, as we say? Alex?
I will do it.
Alex.
Okay.
I will time.
Yeah, don't worry.
Time.
Well, first of all, I would like to congratulate you for reaching this point. This has been a challenging year for all of us, but it's most important for you. There were many questions that I have written, but I got just a couple of things that I would like to share with you. Is that I was worried about what you talk about the adaptive family. Do you have to set some kind of error margin in order to detect the different shapes that you could find in the cloud of points?
So regarding extracting information, I think obviously we wanted to get something there, but we identified quite a few errors. No, so we were assuming on our development that the catenaries are straight, no, like from top to bottom, but that obviously is something that doesn't happen in place. No, so we had errors of the axis of the catenary being moved or just collapsing. I mean, we have identified, so on our validation phases, we have identified those errors. Obviously, it's something that probably needs to be developed further. But also, when we discussed it with Altimetries as well, what they said is like, we want sort of like to have an inventory. So the error on this type of situations wasn't as important for them as basically knowing that they had a catenary there.
Yeah. I didn't. Sorry, but I wasn't able to translate to you the question. What I wanted to know is that you were thinking about a transition between reality and the model. But how did you set the limits of maybe for angle, just to compare that it is just to change that kind of catenary post, that it is oblique and it is not quite vertical. So did you have a limit just to realize that it is a catenary post? Let's say that it may be 2-3 degrees, but no, once it is 15 degrees out of the verticality, that's not a catenary post.
No, so kind of as we said, like the information was already pre-classified by Altimetry, so we already knew that was a catenary. So within their tools, they already have a classifying method for the point cloud. So that was already provided.
Okay.
But even with this situation, I think, but we can extract more, we can test the points to validate really the thing. So we can always think methodologies to validate it with different points, geometry points in the catenary or in different objects.
Okay, and just the last one, okay. Yes. Which was the length of the stretch that you analyzed?
We actually haven't checked because we were working with 2 or 3 point clouds, different point clouds, but I would say it was about 500 meters or something like that. But we tested, as I said, we tested in 2-3 different point clouds, and it worked well, and the running time is negligible. So I think we could have done it in several more. Fairly easy. So
let's say that it's quite easily scalable.
Yes, yeah, definitely.
These 500 meters to.
So as I said,
in the process there are job that done in breakdown. We have the global file, and after we have to split, and the treatment is done just for the elements. If we have 10 kilometers, it's the same thing because the information is looked in one element, and not it will. We are looking for the parameter for split parts. We are not looking parameter for all the linear.
And also another proof of that is that I ran the Python scripts in this computer. If you get a supercomputer, I cannot imagine. So really, like we could handle point clouds. It buffed a bit, but fairly easy. Could be scalable and being done in kilometers of railway without any problem, I think.
Okay. Thanks a lot.
So it's maybe more like a comment. Maybe the question could be whether you agree or not, but I think you should be more confident about the future of it. In the future, the data will be more cheaper and we get them more rapidly. So we don't need in the future for special trace for that. They are developing scanners can be mounted on the bumper of the train. I don't know how it's called, and you can get fast data and every day, every week. So that's a real digital twin. And for your method can be the basic of change detection. For example, what Alex just mentioned, whether there is a deformation of the post or not, and you can measure it in every week by week.
Yes, we can imagine a live link of data.
So we haven't talked on cost effectiveness and so on, no, but when we discussed with Altimetries, I think the plan from SNCF was on trying to pass on all their railway network at least twice a year, so they could have, well, imagine the amount of data. And if you imagine from the previous process, what you had to place is, I think we've done like 60 catenaries, no, as we said, in no time. You'd have to have a manual modeler recognizing the element, placing the element, and so on. They can take a minute, but that'll still be 60 minutes. While with this process, with a bit of improvement, you'll have it in a minute, the 60 catenaries. So we're talking about catenaries only, but if you consider signals and so on, is obviously, I mean, 100 times much more cost effective on placing the catenaries over automatic. No, that's not the benefit.
Yeah, maybe one each. Hey, one each. So
I have no question. I will have a comment, but first of all, congratulations. It's really technically very well elaborated project.
Thank you.
So it's good for that. But my point of view is that, like, as a graduate of this program, if you have a customer, for example, you're working in your own company, if you're working as a digital transformation manager, let's say, how would you describe not Altemis of Spain, like Altemis of the Netherlands, that what are the problems that are going to face, how they will be dealing, or how you can convince them to transform their processes into this digital twin at the end? Like, did you discuss among yourself, if you, besides taking all these problems, you have chosen solved it very well, but how you market this for yourself in the future?
That's it's make grow the active that the asset grow the activity. They can control better their assets with this solution, because right now don't have the digital, they don't have the asset digital. That means that can control better than right now. If you have the asset digitalized, you can control better their own job.
Just simply doing an inventory.
If I will ask them, what do you mean with digitalized?
That you can control it. You can control it.
What are the problems for it? How I can approach that? Like, these are maybe the things that you will need in the future, you will be facing for your customers or for your company. When you say digitalized, most of the companies don't have any clue what does that mean. Like, and then setting up you already really laid out all the digital problems.
It's just having it's just changing an inventory, which right now is a list, to a digital asset. So basically something that you will be able to see, to look into, or to inspect within the digital world, let's say, instead of having a list of all the elements that you have on site.
Yeah. Right now you have an Excel table, and right now you have a model that you can see in object in geometry.
So I think that's the improvement.
And
This is
I want just to add something for the Excel file or the Excel sheet. Behind there are people that move to the site and the inventory of the element. It needs a lot of time, a lot of resources. If I explain I am a BIM user for FH company, if tomorrow when someone came to me and explained me that I can economize time, money, with safety, without sending people in site, and he can just with an algorithm creating a BIM model, I will be very happy, and I sure will be his client.
Even you can mix different data, not only the asset. We can add different data, that temperature or whatever source of information that you can control, and all the time.
Thank you. Thank you.
Simplify.
Sorry. Sorry. Yeah. I will give the floor to Christian.
So, first of all, congrats. It's a really nice project, and I would really advance an idea that you can publish it in a computer science journal or conference. And I know these conferences, your work is publishable. And I will ask the questions in the end because it's a very simple one, but some suggestions for you. When you talk about AI, you are talking about recognizing an object, even if it's an basic AI algorithm, a regression, or a very advanced deep learning method. It doesn't matter. You have two parameters that you need to present in the end on the results. First is the accuracy, and the second is we confuse them all the time, precision. So when you present such results, always have a graphic or have these results. You can say we have an accuracy of 98 point something percent, a precision of 99. Those are false positives, false negatives. We don't discuss them here, but that is the result that a computer scientist would look in a presentation.
So in this case, as we presented, so we haven't in our method we haven't used AI. So it's based on AI information transformed by altimetries. But because of our backgrounds, we were not confident enough on jumping onto an AI model. So that's why we haven't used it. But obviously, there's other implementations where AI could be used, and also further implementations of this after. But yeah, we will consider that for our future projects.
Yes, I just want to add between each phase we add the validation phase. The validation, unfortunately, we cannot go to the end of the process, but we tried to measure and quantifiable the precision of the model.
Those results should be presented in a graphic. So that will have been perfect. I appreciate that you have a clean presentation, and what I would suggest you is that you keep your talk very simple and natural. Victor, I hope I don't mess up the names. You talk without any kind of notes, and that is great. And I've seen that Fuad, Georgi, and Beatrice, during the questions and answer sessions, you also answered in English and had a very coherent speech. So leave the notes aside. It's better to be natural.
Now we have just try because each of us represent the part of the other. We are presenting. We are not presenting our part. We decide to present in order to have the occasion to look or to the job of the others. We take the decision that to present the part of the other. That's why we were somewhat confused.
Did you say that to us at the beginning?
No, we haven't mentioned it.
Exactly.
But we know what we have presented all, so you can answer or you can ask us about anything.
A good question to understand.
And now the question: who has done what? What are your roles?
Yeah.
I see visualization, data extraction
on each.
So basically focused on the extraction part mostly. Fuad was helping me out on the data validation as well, and doing in parallel all the checkups on whatever I was extracting. Julie focused on the inventory of families and so on, which was huge from altimetries. We had to look into that, and then developing the new families that we were doing. And then Fuad also focused on the automation with Dynamo and the validation parts as well. And then Beatrice focused on most of the reviewing part as well. So it is true that in each session that we had, we presented the information or the progress to the others. So we've been quite we knew what the others were progressing on, and we were actually helping each other changing ideas. But that's mostly the work that we've done and how we have split it.
Thank you.
Thank you, Angeli. Maybe a last question or comment quickly for
very, very well structured project. I was just wondering if you had 6 more months to spend on the project, since you rely on the on knowledge about the object that you are trying to identify. So you have strong geometrical information, so you know it's like a catenary, etc. But if you have to develop a scan to beam project on some objects that you don't know, or that you have a very huge list of different objects, how would you extend what you've done to more complex setting?
The great thing that it's a discipline or sector that there are classification of objects very clear. So we can develop a methodology of each object because generally there are a specific object for that.
So you would do it separately for different kinds.
Yeah, and maybe it can help us to explore another sectors like roads or aviation, because it's not only it's an object that we are studying, but this is a methodology that we can explore in different sectors.
Okay, thank you. Yeah, so we haven't done the conclusions, but we have to go fast on that. So,
Thanks again, all. Yeah, okay. We can ask maybe Nicola and Nick to come, and Kilem if you want to come too. And we do like a 5-10 minute break to install the computer of the second. Yeah, I know, but yeah, it was like a noise. Which computer, guys? We need the computer.
or are you going to be using this one? Yeah. Do you have a pen drive or something? I have an external drive. Yes.
Okay, it's better like that.
Yes, just so the group, I just want to see the character behind.
Mais à côté du lien. Rien fait, hein.
Okay, ready, guys?
Je sais pas si on va être sur la photo.
Up. 1, 2, 3. Perfect. Thank you.
Thank you.
Thank you, guys.
Thank you very much. We are late.
A ver, sí.
Hello, Luis. Can you hear me?
Yeah, I can hear you. Good afternoon.
It's very loud. It is very loud.
Yeah, but I can hear you perfectly.
I don't know if it's working.
Yeah. Can you hear me as well?
Can you hear me?
Yeah, I can hear you. I hear a lot of noise around, but I can hear you.
Yeah, I can hear you too now. I will stay like that.
And you can hear me as well?
Hello, Loic. Yes.
Okay, great.
So yeah, right now it's very loud because we have everyone is talking, but I will ask to be quiet for the defense. Sorry, we are a bit late. Okay. Sorry about that. We will start in 5 minutes.
Okay.
Okay, thank you very much. Sorry about the delay.
Bye.
I should have like 1 hour. We I have to open it. Yeah, we can.
No, but what it means is that if you are going to introduce the Scrum project.
Yeah, free, yeah. I understand. No, no. Yes. So we are back.
Yeah.
Can you hear me? Yes.
Yeah.
Perfect. Perfect. So we jump to the second Capstone defense from Eurobios company. And I will introduce Maxime Guéguin from Eurobios. He can just introduce himself and quickly in few words about Eurobios. And then we'll let the floor to the team.
Yes, thank you, Matthew. So yeah, Eurobios is a part of a management consulting firm, and we act as an innovation lab. So we work with our clients and then we bring some solution based on data-driven approach, artificial intelligence, and simulation modeling. And among our activities, we work with industrial asset managers, and we try to develop some algorithm to help them to make some decision about the networks, like maintenance or refurbishments. So that was the starting point of the Capstone project, and it was a pleasure to supervise it during this year.
And we have also Loïc Landrieux online with us remotely, who is acting as academic supervisor. So I give the floor to the first student who is talking, and we need to share the screen. Yeah. And I will just put the Java here. I think it was better. If you see me with something like that, that means you have 5 more minutes, 5 minutes left to keep the schedule on time.
Great, that's great.
There is
So, may I start?
Yeah.
So, good evening, everyone. We are the Europeans work group. I am Juan Manuel Aguado. And well, we are going to talk about the reliability of this data through multi-measurements, remote multi-source measurements. So, what is this? How we have structured this presentation? We are going to do a brief introduction with the objectives that we set up, the timeline, how we work, we have done this work, the workflow we did, the tools and the technology that we employed, also the data collection from which we develop our models, the terms and definitions that we employed, like MVP, the development of the digital twin that we have done, the representation of course, and the applications that we left open. So, well, what do we intend to do with this? We intend to detect electrical pylons. We received a set of locations of pylon from LTE, and we intend to detect these pylons in the territory. For this, we saw two alternative philosophies. We saw the philosophy of scanning through 3D point clouds, which was a very time and resource demanding approximation to the problem, because mainly the classification and detection and reconstruction of a pylon isn't even for a computer, and also isn't free of penalties. Like, for example, it tends to have problems with the detection of the vegetation and including them into the model. And so we opted by detecting these pylons through 2D orthophotos. 2D orthophotos are rid of problems such as lighting, variables such as lighting or the soil where the pylon is ubicated can make more difficult to detect a pylon in certain environments. And why? Why do this? Why to do this? Well, it's there is a clear reason, that is maintenance. We can do preventive maintenance through the visualization of these pylons, knowing where the tops of the pylon are, can prove to be useful in order to detect movements that aren't predicted or usual or normal in a pylon, and detect its if its structure is failing, and also it can prove useful to detect that vegetation is getting in the zone of the power lines. So how can we do this? To do this task, we resort to using CNN. CNN, a convolutional neural network, is an algorithm that it's tuned to detect correlations that are non-linear, and so to detect certain patterns that we want to endorse. These patterns, in this case, is a pylon. Electrical pylon in our but this CNNs has been used in artificial vision through other industries such as transport or medical. We then developed one CNN. We resource to use one open source. The one we choose was YOLO developed by Ultralytics. This CNN, this convolutional neural network, is proven to be used across multiple industries and to be flexible enough to us to introduce certain parameters to ensure the visualization and posterior location of the pylons in order to build our basis for the digital twin. So, as I said, the objectives. The objectives were clear: to train and test a convolutional neural network for detecting and classificating the electrical pylons. Modeling and visualizing the pylons that we have detected could be carried on by a model with GIS. In this case, we use ArcGIS and use a 3D model with model a 3D model in order to make the visualizations. And how do we do this? Well, we have an input of data provided by Eurobios that was consistent from a mix of imagery from orthophotos and satellite imageries. We processed this raw data that we obtained from them. Then we trained the machine learning algorithm. We validated the model. And then we constructed a BIM 3D model. And the last one is, and the last step of this process would be to represent the information that we want in this 3D environment. And so.
So now, in terms of the business objectives, the idea was, well, we have this digital twin. What can we do with that? How can we make this digital twin fit in the real world? How can we find a way for the digital twin? And well, the first idea was the model itself, no? But there are more things apart from that. On one hand, we have that we have got the sense of which is the size of the resources that we will need to develop the CNN model from scratch to get the results. And the other thing is that to get the technical know-how from the beginning, so to be able to well, to tell a client or to tell the infrastructure manager how can develop it by themselves. Another further objective was to have an idea of how this digital twin could have an impact on the resources of the company to do the maintenance works. So how can we save resources? How can we avoid health and safety risks? And the last objective was to get a digital twin that was based on in a GIS environment, so that saving all that information in one layer that could be compatible with other sources of information, that it could be developed for further applications, and that we could provide that value for any company. So the process was no, that way. So the way that we organized the work over time was first of all see what has been done in the CNN and object detection world, which have been the models that have been developed. So once we have clear which is the model that we are going to start with, the machine learning model starts. You can see that it's the main block of the project, and it has taken a huge amount of time to develop it from scratch. So we needed also the BIM model of the electric pylons. So once we have that, we start working on the GIS environment. Later we will explain how we started in open source environment, and later how we finally developed that so that we could take the BIM model and put it into the GIS environment. And the last one, of course, was to write the thesis and make the final adjustments. So this is more or less like the big picture of the whole thing. That could be divided more or less like in three main blocks: the data collection and processing, the machine learning modeling stuff, and finally the digital visualization in the GIS environment. So we start with raw data. We start with 3,500 images and 6,000 pylons that are distributed over France, and they have their annotation files with them. So these annotation files were JSON files. So we had to process all that information. So translate that information into the files that could be read by the model. So 90% of the annotated information was given for the training of the model, and 10% was given for the validation and the testing of the model. So once the model has gone through the training, testing, and validation process, we get a final model. So the final model is the best fit that we can get in terms of some parameters that we will explain later what they consist of. And this final model is the one that gives us the results of the pylons that we take. And also, along with the BIM model, we have built a Python script that reads all that information and starts feeding the GIS model with electric pylons in France.
Hello, you all. When we're about to start to develop our project, as you may guess, the backbone of the project is creating a artificial intelligence model, which is search about all around the France. And it was needed to be deal with a kind of big data, such as thousands of kilometers squares. So we needed to decide which way to develop that model is more efficient and give us the best results that we according to need. Because of that, at the beginning, we started to do some tests with small data sets. We had to set a standardized process because comparing the things, we need to know which one to best for us. We had two options: using Google Colab or continuing on our local personal computers. They both have advantages and disadvantages. For instance, standard PCs or laptops is far better than Google's Drive, Google Colabs or other cloud services provide you better CPU resources, because the service, all the cloud computing servers are using the Intel's most efficient processors, not about the best performance. Especially in the detection phase, you will need to CPU power, but during the training phase, you need like GPU power. So we try to train our model on the GPUs, Google Drive. It's let us to work on NVIDIA A100 GPU, which is most cost like 15 or 13,000 euros, I don't know. And also hard to get for your computer. And they let us to work on this instance just for 50 cents per hour. It was let us to gain more time, as you see. Training time on standard PC and regular GPU card is about 7 or 15 hours. Depends on the size or detail of the model. But on the Colab, it takes like 1-2 hours. As a result, 7 times faster than. And also the cloud computing resources provides you more stable platform to develop your model, because whenever we try to follow our training process, personal computers always gives an error. Somehow, due to the platform that you're using, because you cannot directly open a notebook or anything from your computer, or personal CPUs might be include some errors. all the cloud, unless like that, cloud environment always optimized accordingly because they are already set for efficiency and reliable. It led us to like 24-hour doing 24-hour long trainings. Also, it's scalability. You know, we cannot get, according for one project, we cannot buy two GPUs, but if we need, we can go just open a new notebook through the Google Colab, and we can run another model inside of it, and it will for sure speed up the process. Uncontrollable costs. If we set our algorithm like lifespan, time span, it will just work until then and then terminate by itself. So it's led us to decide on the cost, but how much we want to spend, and during the checking the results, by the way, even if you want, you can just set the limit of the precision and waiting for that call, catching that precision. Whether you can set the limit of the time. And computational power, as I said. So we decided to start on Google Colab, and before the train our model, we had to kind of structure all the resource that we get from Eurobius. They provided us like 3,500 pictures, which is annotated by all the key points, like 4 foot of the pylon, 2 wing, 1 head, and middle of the bottom. Like that, they let us that, as you see, 8 key points. These were from 2 different satellite images. One was half of is from UP40T and 42, and other half from IGN. Those were different resolutions. Like IGN was like 20 centimeter resolution per pixels, but UP42 was between 30 and 50 centimeter per pixels. So we turned these key points to we can feed our algorithm, because our algorithm didn't work just exactly like Eurobius did. Their annotations was in the format of another language for another developing model. We just write a Python model that turns that into our we can use as our model. But thanks to that, we just get rid of the process of the annotating, which is most time consuming things about this developing this kind of project. After that, we try to use our JH coding system. We need that because we had to uniquely name our pylons, each of the pylons. We are going to more than 300,000 pylons scan. We about to try to scan 300,000 pylons. So we couldn't name that like RT did, which is French Electrical Distribution Authority. They always made them line named they like according which line they had tables accordingly which number, etc. But we just needed that shortened name that as much as we can for make steps make easier. So we use the JH coding system. This identifying is refers an area, not a point, unlike our X and Y geographic referring systems. But each steps increase the precision of the tail. As you see, the first letter is just you can choose any place of the word. The second place, it's go button of that. When you reach around 8 digits, it represents like 50 centimeters square meter. We use 12 steps because we needed to refer our pylons foot to. Each pylon is now referring as 12 steps, and it leads to like millimeter sensitivity of millimeters. So we change the pylon's name, we use the Eurobius annotations, and accordingly, because sometimes in the picture there was many of the pylons. We fixed all of the problems. And other things that we had to care about, it was distributing the training data sets. Some part of branch might be more force, or some part of might be more, it's changed the bottom of the base of the picture. So it causes not detected, not trained. Because of that, we try to divide the branch to equal subcategories. Then we collect the training categories between those subcategories. Each subcategory has own training and validation dataset. This validation is another step of the training, because after the training the model, you have to validate it by another set of the data, which is not included in training process. It was just for validating. So in here, we just try to show the distribution of validation and training dataset. The highest values is close area of the like Paris, Lyon, this metropolitan areas includes more training, more finance data than others. We separate like that. It's most common to do that. 90% of the data has training, 10% of it like validation. To be honest, normally they are used like 70% as training, 20% for validating, and 10% for testing. Test data is not included the annotated data. But we just wanted to use as much as we can. We didn't use the test data, and because of the 3,500 annotations, we just thought that 3,000 would be enough. Now I will, before to dive in detail about the machine learning results, comparing, I had to talk about some metrics about the shows precision of or how success are modeled. First one is MAP. MAP value is mean average precision. It's just those values get it from training during the training phase and thanks to validation set. When you train the model, it tests itself with validation set. Then check the results. If you already have two of the annotations, and if there is any mistaken, like overlapping the boxes, actual boxes, this one is used in training or annotated by a human, and this one is detected by a model. So when you overlap them, it calculates the overlap area. If it is more than 50%, it's accept that as true. So after the continue to process, like predicting, giving the competency score, etc. This precision value is valid for overlapping more than 50, but this 50 and 95% means from 50 to 95. It's step by step increased and get the median of that, mean of the total. In here you see the false positive, the confusion matrix, which shows us where the pylons detected at pylons or anything else or anything, some grasses detected of pylons is false negatives or true positives, this kind of things. We didn't put that graphs onto our presentation because we had only one class, which is not meaningful to show that in here because already it shows the result of the precision of the model. It's not good to see that because you can check this better for confuse if the model confused between classes. Otherwise, it's just is it work or not? Matter of the word. Then there's a hyperparameters batch size and epoch, which is I will go dive in more detail. Epoch is the term of that how time models, when models see all the data sets, training data sets at once, it means one epoch. So sometimes it can be, confusing by iterations, but it's not iterations. Iterations is size of the samples that used in the model, developing model. When you all the samples are used in the model, it means that one epoch. So epoches consist of iterations. You see here the learning curve. As we as we train our model with more epoch, it means that the layers are become so much, and each time it develop it by itself, increase in the performance. As you see in the this learning curve, but at least there were nothing to left for learning the model, so it will be goes too straight. In here, it's not that straight enough, but we just process because it's too long, and that increase of precision was not matter for us. But increase the epoch, you have to take care about that being overfitting. Overfitting means your model going to run. It won't detect the new data sets, new data, and just will focus on what it's learned about. So you have to find a place that's most efficient way and according to your needs. For instance, in here we reach around 85% of accuracy, and after the training model with more epoch, it will just cause overfitting. If we add unless 150, add like 150 more, make it 200, it will just make a difference like 1%, perhaps. So according to resources, needs and precision that you want, you just have to set the limit of the epoch. Mostly commonly they are using 200 or maximum 250, 300. Yeah. In here, the image size. Image size is important for us because we are going to deal with GIS data. GIS data was provided by IGN, again, French authority, that took the orthophotos with 20 centimeter details per pixel. Each photograph of each image of the set, that data set provided by IGN was 25,000 times 25,000 pixels. When you try to read that picture by your model, which is it will be consume a lot of RAM, which is none of the usual computer I don't think would be handled. In our algorithm, it uses like when you train for 2000 pixels, it decreases the size of the picture to 2000, then start to work on it. But if you decrease a picture like 10 times, it will loss of the information and nothing will be detected inside of it. So matter of the image size is dealing with that big images as much as possible. So you have to increase the image size, but there is limitations like GPU memory. If you increase the picture size, image size, model training model size, it will lead to consuming the GPU memory and also duration of the training. So we did our best because we just try to fit as much as we can. But anyway, it's still not being more than 2000. In here, we just try to show that doubling image size cause like 3 times more GPU usage. If you go to like make it exact 1000 or 1300, it will be it won't be fit in the best GPU in the work that produced. So again, it's matter of the needs and resource. If you're going to just check something on live or HD image, it depends on the what you want to scan. If it is like us, it's bigger images, you have to train a model as much as big you can. In here, you see the batch size. Batch size means how many of the samples that, because we provided 3,500 pictures, and that 3,500 of them not just at the same time is learned by the model. It just selects some of them, augment it by itself, and then try to learn that, creating that tensors, this kind of stuff. Batch size, increase or make it more or less using the sample size in each iteration. I mention about the epoch. Each epoch was consisting of iterations, and size of the iteration decided by the space size. So, as to sum up, batch size is the way to fit your model into a GPU. Normally, it's accepted as 16 in our algorithm, but if it's not fit in your GPU, you can decrease it to 8, and it will be half consuming of the GPU. But it makes it longer because it uses a smaller part of your instance, your data, and you have to make more epoch to gain again that amount of the precision, like B. But anyway, it can be useful when you have limited resource, like when you have to try train a model on your computer. You can play with these values and make it run at least, because in my computer I couldn't even run the model without the decreasing batch size. Even it fits, you have to make it much less to work more confidentially. In here we are seeing model size. In our algorithm, it starts from nano to X large. It means that how many layers inside that model. When model gets bigger, it means that there are many options, many of the possibilities that calculated by model, but it leads to consume of the CPU, as you may guess. According to need, if you need to make the process faster, you have to decrease the size of the model, use the smallest model as you can to make it fast. Also, it means that with if you don't have any powerful CPU, you can you make your size less than usual. So in here we compared the two models, that largest model of the our model and smallest model, and there was 2% increase as results, but more than 5 times time consuming, because they have 32 times much possibilities to calculate, as you see. It depends on, again, it depends on your needs. If you need more, 2% accuracy is more important for you, you have to wait 5 times more. Whether that small one is already can be acceptable. Yeah, we did a fault. We did some mistake during our training. We just figured out we used wrong data set. Like we had created Euroboost provided us 3 different dates of the images. So this means that in same Python, there are 3 different angles, 3 different data. They took another angle of the images. It makes you to made a more confidential model, because in that pictures when you provide other angles of it, it's learn about how the statement of all angles. So it will increase the performance. But when we try to separate our data set as training and validation, we didn't figure it out at the first. We just make 3 of them to delete. So 3 times the model used the same picture. So we didn't use the other options. It was like, I can't remember, no. It was like 300. We just collect out of the 300 pictures of other angles, like 10% of the whole data set. And we didn't figure it out. It will still give us a precision of 93%. When we figure it out, we fix that problem. We include those all angled pictures inside of the training too. And as you see, it was significant increase. Never any other hyperparameter can pass. So as you see, epoch was it was faster than it, and also consuming of GPU was nearly the same. It means that you have to be careful about when you're preparing, because even if you do a lot of the training to compare all the things, just correcting your data sets is better than anything else. At least we decided to our best models. We used the largest model of our algorithm because we don't have the limitation of time. We already had the statics images of the Earth that took them from, orthophotos satellite images like that. So that 100 millisecond differences was not affect us. Because of that, we just choose the largest model as we can. This one is better, especially for live streaming detections like sport match. If you do sport match, you have to be fast because the frames are flows. So you have to be as fast as you can. But we don't have rush, so we just choose the more precise model and largest one. We did 135 iteration. It wasn't selected. We just set the 15-hour limitation for training, and it was reached to 135 iteration. We decreased the batch size till 5 for fitting the GPU. As you see, GPU is consumed like 39 gigabyte key. Our GPU had 40 gigabyte. Even if the 800 megabyte increase in the data sets could corrupt the process, interrupt the process. And image size was 2016. The 16 was because of the, it had to be power of double 2. We used, to be honest, we decided the batch size according to image size because we needed to scan as big as we can. But afterly, we had to divide our main pictures to subtiles. After when we decrease the model size of model, it lets us to scan less tile and create less tile. So we just try the best, largest image, train our model according to last images. Accordingly, we decrease the batch size for fitting the GPU. So all things kind of related with these hyperparameters. You just need to set your needs accordingly, change the hyperparameters and resources, of course. And this combination gives us the best result that we can get. Now,
yes, 1 second. Because it seems that the setup is at the beginning. No problem. I'm going to have a commercial break. Should we start to speak about it, Uncle? No matter that I have to. No, no problem. You can. So, after we were going so deep into the machine learning part, and as Juan Manuel showed at the beginning, how our processes were looking like in thinking the timeline. During the point when we have to actually making a big step for visualization of the geometry. Our point was more like this, that we wish to make a 3D model and to show it for everyone who's not so interested in having a deep knowledge in machine learning part, to be more understandable to sell the digital twin part what we were making. We can discuss later also during the questions about it, what kind of model we made. We were thinking about to make a symbolic model. We were thinking about a realistic model. Both of have pros and cons, but we will see later this topic. We will come back to this one. After we made a 3D model, we were like, okay, we want to show it for the people to understand where they are and which environment they are. And as Juan Manuel mentioned at the beginning, we started to use from the beginning open source programs to work easier for ourselves and not to make a vote for one exact program family or supplier. And we used QGIS, and with this one we had a big problem. We really had big problems. It's also up on us. But after it, we planned to make the connection between the model and to place them on the GIS environment. But there it didn't work as we were expecting. And our time was really slightly. So we decided to transform this GIS environment to ArcGIS. And then in that case, I'm want to ask the help of Borja because he was making that part to explain it a little bit better.
Yeah, well, so the idea was starting with a model, what we have called the optimized CNN model, the best fit that we can get, the most accurate model, and getting the information from there, having the B model already built. How can we start placing the pylons in their correct position? So ArcGIS has a Python plugin that lets you run a Python script feeding with all that information and start building the model. So the idea was to build the script, and we started with small tests. So taking just a small amount of information so that the GPU didn't collapse, and we started testing and see the results. So in the end, what we could get was the pylons in the correct position, and that could help to visualize the entire network in just one model. The problem was that there were too many pylons. 6,000 pylons for the GPU was too much. And in the end, the idea was to split the model in the GeoHash code that we explained before, so that the model in the end was manageable. Because in the end, what we are trying to get is something that the client or the infrastructure manager or whoever can manage in their maintenance works. So this in the GS environment, it helps you to locate them in their correct position and also see what are the environment and the elements that are around the pylons.
Thanks, and then I'll take back the lead from this part. Yes, we were spending most of our time to making the machine learning part because this is the basic of our digital twin idea. Unfortunately, we didn't have that much time and resources, we have to say it honestly, to develop so far. But we see some further application. How can we use it? So right now we have a process from pictures to build up a system of 3D models, and we can upload it with data. The only question is for what I want to use it. It's all question of maintenance. Which type of data I want to upload it into? How should I use it? So technically, we were thinking about the further usage of this model in 3 different ways. First one is what we created, how to use it in different infrastructural sectors, for example. The other ones is, for example, how to evolve, how to use and make our digital twin to the next step. And the third one is how we can, or how we have to change the machine learning model to reach something different. So another goal, so maybe a completely different sector we also can try. So for example, to stay with the first one, we can merge much more data. So we also can include wires for it to build a whole system, to show the vegetation. It depends on how we want to use it in that project exactly. But the same technique and logic we also can use in railway or in road infrastructure projects, or for example, to also for the wires or the catenaries to show them and giving and detect them, also the pylons there. And also for signaling, it's a really easy way to interpret our idea to different type of sectors. Of course, in that case, we also can think about it. Maybe the road signs we have to automatically make it and to show it in a digital model. So we think that our model what we made is a good base. On this base, probably we can make a whole system, a whole network, a grid network. We can make also different type of simulation. What is when there is a power outage? What is when there is fire in the system? How can we supply the rest of the city with enough electricity? Which routes we have to not to break the complete system down? And we also think about it that, for example, we can help for civil organization, for example,
the forest protection or environmental protection, like these birds are also unfortunately running into our system. And we can give them also data and information, where to go, how to go, because our idea is like that. We have the model, and if we put IoT devices on it, we can measure anything what we want. It depends on for what I want to use it. For the machine learning part, which direction can we go? We can make an automatization, not just for pylons, that, for example, state companies are building their own digital infrastructure by it. So this machine learning result or model, what we were building, cannot only use for this. It has really big depth to move it to other sectors as well. And we also were thinking about when there is a first and rapid assessment of damage in the infrastructure, we can also progress or to teach a new machine learning methodic to see the first picture, checking the new one after a disaster, and what happened, how big is the disaster, what kinds of damages we have on that area. We also can turn our machine learning process to this direction. And I think that was everything what we wanted to show and explain for you. And thanks for listening to us.
Great. Thank you all.
And thank you, Luis, too, and Maxime and Loic. Their support has been good.
Thanks to Maxime and Loic. Where we can have the question from the jury. Who wants to start this time? On the right-hand side, maybe. Hey, Jeremy.
Thank you very much. So the presentation was very detailed on the machine learning part. So I didn't get if the annotated images that you had only, so they had the pylon name, or you had annotations were different kinds of pylons depending on the type of equipment, etc.
Yeah, it's just including the wing of the pylon, top, and K points. So some 8 of the K points, not other the information about the type, class, other things, or voltage. We can get the voltage or height something from the RT data set, but the set that we get from Eurobus was only about the K points.
Okay.
And by 8 points.
And when you discussed about the precision measure regarding the overlapping of bounding boxes, etc. But so you also learn the position of the key points in each pylon. So did you check the accuracy, not just the bounding box, but also the geometric information about the different key points?
That matrix that I showed was about the bounding boxes, the binding pylons. It wasn't about the K points. The K point has another matrix that gives you, but it's not accurate. It always shows 99, but it's not that always correct. I can just visually by myself can say it's 50% succeed to find the key point, which key point is correctly in its place. The problem is that some key points are not visible. Another challenge was about that, because in algorithm that we used, you have to enter the coordinates of the K point according to picture, and also you have to show enter the information about is it visible in picture or not. That was another matrix too. If there is a right or left side is matter, you have to change the flip. There was flip index, many of the flip index in our pylons. If you want to classify them, it would be useful, but we just accept that all of them like pylons. We didn't separate according to their shape or height. So there was many other metrics that we didn't use because we just focused on our finding and key points, as I said. That some of them was not visible, but we just exact all of them as visible to increase the performance of the model. If we had to back check the whole annotations, then started to annotate it again from the beginning, to which one is visible accordingly. We just try to not enter that part of the work. So we could increase the performance for finding key points. Some of it was still giving like 50–60% of the accuracy to correctly find the points. It exactly finds the visible one. It's much more than, but other invisible parts could be tricky. It's missed.
Okay. Thank you. Some questions, comments from your side? Anyone? Bilbo, can you go in the center for everyone to see you when you answer the questions? No. We can see you, Salisha. Yeah, you have to move like. I think it's fine. Yeah,
it's a great presentation. It's very well structured, and I like the idea of business, like setting business model objectives, technical objectives, how you define them. Two questions, maybe I didn't get very well. First one is this your model of machine learning for this model. You teach it with 3,500 images. Can this model detect pylons in, like, if you go with drones and then pick up the images? Like, can your model detect from the frames of the pylon?
Yeah, other remote, yeah.
Yeah, other remotes, the pylons.
It can, but it depends on the distance of the the image you get caught, because we learned from our machine learning courses that this algorithms made tensors, and this tensors includes some height information according to picture when you look at the picture. So if you train your model like for 5 pixels, and then if you show it could be acceptable unless 6 or 7 pixels. I'm not sure about it. I didn't check that. But if it's been 20 pixel picture object inside the picture, it won't detect it. If you want to detect all the size, you have to variate your data source accordingly. You can make zoom in, zoom out, then it can detect. In our case, you can use that in drone, but you just have to be sure about the rate of the pylons inside the picture should be around our models, like we trained model.
It's a very promising that you can detect really.
Yeah, and I can say you can, because I know the height of the drone and the tail of the image, the pixels. I can say you can detect. Even the live streaming, you can detect. It will still works.
And the second question is, you mentioned that the CPU was not enough to calculate 6,000 pylons. One of you mentioned that.
On the AIS model.
Yeah.
It was just to. Yeah, sorry.
Then if it's really not strong enough, like powerful CPU, then how we are going to manage to build the digital twin running it?
Well, that problem was because I was using my personal laptop. I mean,
Okay,
if I were using the GPU that Salican was using for the machine learning, that will probably handle the entire model without any problem. So the problem, the only problem was that I was using with that limitation. And that's why we decided that work was already done of the GeoHash classification of the pylons. It was much easier to group the pylons in those areas, but with larger capacity of GPU, which was the only limitation, probably can handle the entire model.
Yeah.
There are many more technologies that you can share the load between the GPUs, other instance, NVIDIA and AMD build that technologies. Even if you had struggling with those kind of a lot of the images that you can handle by one instance, you can share the same workload to other instance, which is we couldn't do because we just used the Google Colab. Google Colab just gives you one instance to use one. Just you can think about one computer that you can use. We just try that, make it multiple. We just scan the same input with different computer. It was not cause any problem for us. But for further application, it can be used like Amazon or Azure instance, Amazon AWS cloud computing system because they provide you much more powerful GPUs, and you can make connection between them. This for the application and the
That might have been great. So you were applying both courses on cloud computing and also artificial intelligence at the same time.
Yeah, exactly. Really we benefit from all the courses nearly. It's all happening.
I have a question. Can I use your solution on a country or another continent where the shape of the pylons are not the same?
Yes, you can.
But you need to know basically the shape of the. You need some configurations at least.
Yeah, but if you have the images to train the model and you have them annotated, you can feed the model these images
you have to train again, and
then you can.
I mean, I got an idea for that. I mean, you might generate your own images synthetically, so they are not real, but you can generate different pictures randomly, and then you can either be trained with synthetic pictures and then use real data to see if that works or not.
I asked the exact same question to our academic advisor. He said it won't work. Thanks to Rick. Hello.
He's not here. He's not look back.
I'm here.
Yeah, Loic, we can hear you if you want to add something or ask a question.
Maybe. Just a quick question, something I don't remember. In your machine learning model, your model draw little boxes around the predicted pylon with a number on top of it. Can you remind us what the number is?
The number which is drawn around the box.
Yeah, on top of the box there is a number between 0 and 1. Do you remember what this number is?
Yeah, you mean confidence rate, aren't you?
Maybe, yeah.
Confidence rate is how a model is confident about its founding, because when you learn to train the model about an object, it matches that it learned and that's what it found. So that we can show it.
I think it was 87.
No, 90. It's
So what does it mean exactly? If it says 87, is it going to be correct 87% of the time?
We couldn't say, but we can say that model is confident 90% about its pylon. It is fine.
What does this mean, confident 90%?
Let me show you. Yeah. 90%, yeah.
Yeah, what does this mean if the model says 93?
It means that the match of the models trained, the tail of the model trained, and what it found from the picture. So it's kind of matching what you learned and what you found. Kind of. And
do you remember how this number is calculated?
No.
Okay. Okay. So you said at the end, in future direction that your model could be used to do predictive maintenance. Can you develop because the machine learning model, if I understand correctly, is an object detection. How could you expand an object detection model to do predictive maintenance?
So if we feed the model with more and start using really and comparing historical data, we build a database with the points that we are detecting about the wingspan and the basis of the pylons, we can start measuring little movements. If we start measuring these little movements, we can start predicting if the pylon is going to fail. That will be the basis to build predictive maintenance in this case.
I hope the pylons are not moving enough that they're measurable on satellite images. Otherwise, I think it's not predictive anymore. It's your pylon is kind of destroyed. But basically, you would need to build a predictive maintenance model on top of your own model. Okay, last question. Let's say I have my own images with pylons, and I want to view them in QGIS using your thing. What do I do? Do I have to install a library? Is there a plugin? How long would it take for you to run it on my computer?
I tried it in working in QGIS. I think it's because of the software limitation, because of the Windows limited some usage of the softwares. It's really decreased when you compare it with the Colab. It's
no, but okay. I have just one image. I want to use your trained model, and I want to convert this image into to go from beginning to end. How many libraries do I have to install? Is it easy? Is it hard?
Like as I remember, like 8 or 9 libraries that I use. It depends on nine libraries. It includes to process rastering images, converting the images, because all of the orthophotos images provided us as compressed version, which is cannot scannable by our algorithm. So we had to convert them by a library, then we had to make them onto subtiles with another library. Also, we used our algorithm. There was something that I have to say, because we used an algorithm to develop our machine learning. Normally, you can use from scratch, you can augment your data by yourself, but the data YOLO, that's 8th version of YOLO provided by Ultralytics, is an algorithm of creating a PyTorch model. So
let's say I have PyTorch, CUDA, everything. But okay, so I'm gonna frame it differently. Is there in this world a computer with all the necessary library where you can put an image on it, output something on QGIS, or did you send intermediary result by email to one another? Is there one computer that can do everything?
One computer can do everything, yeah.
Do you have a computer, a real life that I can touch with all the necessary libraries installed that can do everything from beginning to end?
Yeah, some of them you can import. Also, I had to finish about the algorithm that we use already includes most of the libraries. Because of that, when you import just that library of our algorithms, it brings most of the library by itself. So you don't need to import anything else. So there are, I think, more than 10.
Okay, so who has this computer? Do you have this computer? Can you, if I give you an image, I'm not going to ask you to do this, but if I had an image, we could run it on your computer and it would do all the steps until I have 3D pylons and QGIS?
You mean just predicting or developing model too?
No. Just inference, just prediction.
If GPU is sufficient, we can.
On your computer?
Yeah. Yes.
Theoretically, you could do a live demo now where I give you a USB drive with an image and it shows it to me on QGIS. It's really.
We create our algorithm like that. You just need to put the input folder and it will start to process by itself and finish it all.
It might last for 15 hours, but it will do it.
It will take hours for one image? It should take seconds, no?
One image takes, with converting, if you provide us like IGN photo with 25,000 pixels,
yes,
compressed, one image took around 3 minutes. 3 minutes
okay.
To compile, read, scan, then save the results.
Okay.
Actually, we didn't mention about that, but we completed a district of the brands, which is sorry about pronunciation, but it's yeah.
Okay. Okay, thanks. That's all for me.
Completed that. We scanned that for seeing the results. And it was not only for one date. IGN provided us like for different years orthophotos for so we just scanned 4 of them to match the some missing pylons, other things. Already we had the results. It worked, by the way. it worked for SQL. We just pour the inputs to a folder and then leave it to work.
And is it consistent temporally? Do you observe the pylon at the same place, or do they blink in and out of existence? Or
some of them I matched, to be honest, or to see the differences between results. I just grouped the results. In here, GeoHash helped us because we predicted our models according to 12 steps of the GeoHash, but when you group it for first 8 digit, it leads you to collect all the information about the pylon together. So if you group all the founding according to first 8 digits, it makes you to make group all the foundings according for one pylon. So we group them and we see them which one is resulted what. And at least, to be honest, we compared with RTS data for just that stick. If you take only one date, like 2012 images, satellite images, it gives like say 60% of the RTE data. It's matched with 60% of RTE data.
Okay.
It was because of this. It has less resolution, like 50 centimeter. Then, when we moved to 2018, 2021, 2015 data sets of the orthophotos of the A, and combine all them together, it was much more than RT, like 10% more than RT. If you don't count the mistaken, that false foundings, it will be still 1% or 2% that RT didn't count. Not, I can't say didn't count, not including in the RT dataset.
Okay, understood. Thank you. That's all for me.
I think we need to move on for the next episode. So thank you again.
Are you computer science students?
No civil engineer, sorry. No computer science.
Civil engineering. You talk better and you presented better than all of the students that I've seen at our AI master's degree.
I got some kick from the
So you are passionate and keep it.
Yeah, keep it.
Oh, you don't want the first thing. Okay. No, I'm good.
No,
Good.
see that, okay?
It's fine. Okay. Congrats. Good job. Thanks. Wait.
Perfect. Thanks again. We are going to take 5 to 10-minute break, and we have the last Capstone with Edmore and Abba who is connected online.
Okay. C'est bon pour moi?
Thank you, Louis. Yes.
Okay, ça roule. Bye. See you tomorrow.
En español.
We're going to speak.
Yes. Hello. Abba, do you hear me?
Yeah, I can hear you. Can you hear me?
I can hear you perfectly. Perfect.
Perfect. Yeah.
I think I see you connected. Can you? Yeah.
Yes, good afternoon, everyone. Sorry for not joining.
Can you
but,
just open your camera just to introduce Siemens and quickly say a few words?
yeah, it's not working. I don't know why it's on. I tried, but yeah, sorry for that.
We can hear you. It will be enough.
Okay.
So I will introduce you and you say a few words and we start with the project.
Okay.
Okay, perfect. Yes, we have new sheets.
Don't worry about that.
Make it like. Okay, please, thank you. We start with the last capstone from Siemens Gamesa company. We have Edmore and Abba connected remotely. Please. Quiet, please. Quiet. And we have connected with us Sami Zouri from Siemens Gamesa, who is the supervisor for Abba and Eddie. He will introduce quickly himself and Siemens Gamesa, and we will start the presentation afterwards. Thank you.
Yes, thank you, Mathieu. So sorry for not joining physically, but I hope you are having a good moment. So yeah, my name is Sami Zouri. So I'm working for Siemens Gamesa since almost 4 years now. So initially, I have a master degree in data science and machine learning. So I joined the company deploying machine learning solutions specific for wind turbine field. I'm located in France. So the Siemens Gamesa team is located both in Paris and in Rouen. So yeah, not that far from Paris. And we develop R&D solutions for offshore wind turbines. So, and we have an expertise in everything related to fatigue analysis on loads. And yeah, basically we develop new innovative solutions based on machine learning and based also on more advanced algorithm to make our internal process faster and to unblock new opportunities to improve more and more the LCOE, so the levelized cost of energy of our wind turbine solutions. Yeah, thank you.
Okay, thanks, Sami. And I give you the floor. Just I mentioned also to thanks Paul de Glaire from Siemens Gamesa, who is a key partner and helped me a lot for this Capstone project. So Edmore and Abba, the floor is you.
Thanks.
Thank you very much, Matthew, for giving us an opportunity to.
Can you move just in the center? Thank you.
Okay, thank you very much. Good afternoon to you all. It's actually a pleasure for me to travel from Africa to come here and present a digital twin for sustainable energy infrastructure, wind turbines for load emulation and power forecasting. That I'm going to co-present with my colleague Abba, and I will also going to introduce to you our academic supervisor, and also I would like to introduce you also to our industrial supervisor who really assisted us to come up with this project. Okay, to begin with, I think first things first, I would like to take an opportunity to thank everyone who is in this house. Let me begin by thanking the entire faculty of the various universities that we worked with for the mentorship that we received. Then I would like also to thank Sami from Siemens, who was our industrial supervisor from Siemens, for his unwavering support, without whom none of this would have been possible. I think we got some good mentorship from Sami, I should mention that. Then allow me also to thank Matthew, the academic director for this program, for accepting this proposal and also letting us pursue the idea, despite it was not part of the initial plan. I think initially we were given a certain topic to work on, but we opted to look for a solution to address sustainable energy. Since the whole world, I think we all understand that the goal is net zero. We want to eliminate carbon in the whole world.
So we decided to come up with a solution, myself and the ABBA, to say where is the gap. Siemens has been in the industry for so many years trying to address energy supply, but where can we identify a gap and how can we come up with a solution to optimize the operation of wind turbines? Lastly, I want to thank everyone. We collaborated from the onset of the program up to today, and the value of the information or the teachings that we received from each and every one of us, I think it assisted us to come up with this work. Okay, I'm going to give you an overview of our presentation. I will start by providing an introduction about Siemens Gamesa. I think I mentioned that they are a big guru in energy supply and also providing solutions in sustainable energy. Then I will talk about the project, and then I will also why would it be useful for us to come up with this. So it's going to come up with a business case to say what's the gap, what should we do, giving us what benefit. Then on item 2, I will ask my colleague Abba to take us through the data analysis, the data sources that we used, then the universal data analysis as methodologies that we used, and then the multivariate data analysis. And then from there, we will move and to talk about the model 1, which is the load emulator. So our project is in 2 parts, trying to address the structural integrity of a wind turbine, which is susceptible to different loads. So we'll talk about the load emulator, where the model fitting and training is going to be presented. Then the goal being to optimize the model, and then provide a model bias analysis. Then we will move over to item 4, the model 2 power output, which is another goal of our project, to estimate or to do power forecasting of a wind turbine. So we do model fitting, training and evaluation, and model optimization, and model bias analysis. Then from there, we'll move to talk about the results that we came up from all the processes that we carried out. So we'll check the accuracy of the load emulator. We'll also check the accuracy of power output. That resulted in us being able to come up with the best model for power forecasting. Then lastly, the goal being to come up with a digital solution, digital twin, for the load emulator and also for the power output forecasting. Any questions at this stage?
Question of Azim.
Okay, thank you. I'm sorry, I've got 2 pairs of eyes, but I can't properly see when I'm seated there. We're standing there. So I'll talk about Siemens Gamesa. It's a German multinational conglomerate company with a long history dating back from 1847. The solutions that it provides include energy generation, power transmission, industrial automation, transportation, healthcare, building technologies, home appliances, and additional industries. So in 2017, there was a merger that happened between the wind power division for Siemens and Gamesa Corporation. They made a form Siemens Gamesa, and the initial share spread was 59% in Siemens Gamesa, while former Gamesa shareholders had 41%. Then in 2022, the share was then distributed as 100% between Siemens Gamesa. So Siemens has been involved in wind power for decades, establishing the world's first offshore wind power plant in 1991. Then I'll talk about the geographical spread of Siemens Gamesa's operations. I think it operates in 90 countries and generating greater than 100, GW installed in Siemens Gamesa is one of the largest wind turbine manufacturers in the world. For it to keep being competitive in the market, the key goal of Siemens is innovation and also trying to reduce more and more electricity, which is trying to eliminate the carbon output from power generation. So to do so, the digitalization and artificial intelligence are its key technologies that helps to reduce the carbon emissions. And the wind turbine is one of their strategies as a way of eliminating carbon emissions into the environment. So our project consists of 2 AI-based products. That is to optimize existing processes, the existing processes currently at Siemens, and then also to unlock new opportunities in terms of optimizing the efficiencies. So during our Capstone project, we managed to develop 2 AI-based products. We used machine learning based on load emulators based on information available on the fleet. This helped us to predict the equivalent loads of different components of a wind turbine to perform quick fatigue analysis. So this was one of our KPI in terms of coming up with this project. Then the other part was power forecasting, which was based on the environmental data available, temperatures, wind speed, wind direction, and air density. This helped to predict the power output which a wind turbine can come up with. I'm not sure, Abba, if you want to add more on this slide before I move to the next slide.
I think it's good. You can move to the next one.
Okay. So the biggest question that we tried to address is to say, why would it be useful for us to carry out load emulators analysis? And also, why would it be useful for us to do power forecasting, which will result in us coming up with the business case to say we want to optimize the existing operations of wind turbines being done by Siemens Gamesa. So the first item there is anomaly detection, which falls under the structural integrity of the wind turbine itself. So we did that through the diagnostics of cracks and also preventive maintenance. Also, the load emulators product assisted us in assisting in internal processes that are done during the designing of a wind turbine structure. So this was done by, instead of us doing design reviews and more work in terms of the design phase of a wind turbine farm, we used machine learning load emulators, which will save in terms of reducing the engineering working hours. Also, under the load emulators product, we managed to come up with a solution to push up the design limits of a wind turbine structure through fatigue analysis to check the blade utilization and also optimize design life without failure. I'll move over to the sequence of our project. So we initially started with the data acquisition, and data was already available. And what we only did was to extract the data using, which was collected using the IoT tools like sensors. Then we pre-processed the data, which was already available. And then from there, using the machine learning tools, we trained and also did some residual calculations. Then lastly, we came up with the health status judgment, that is the analysis of the whole model training. Then the other objective of this presentation was for us to do power forecasting through the use of environmental data, where we checked the wind farm condition monitoring. We also did wind farm resource assessment and grid adaptation. The long term being to come up with power forecasting, and the short term being to also come up with the short term power output that we can get from the wind turbine. Okay, at this moment, I will ask Abba to take over and present on data analysis.
All right, thank you, Eddie. Yeah, so the first part of it we did was the data analysis. So initially we got data from Siemens Gamesa, and those data are representative from the wind turbine. So there is loads that act on the wind turbine. For example, the first one we have is like the edgewise, which is the bending moments on the wind turbine that is perpendicular to the direction of the wind. When the wind acts on the blade, it results in the blade bending sideways. That is the edgewise bending moment. And there is the flapwise bending moment. And this is the bending moment that is perpendicular to the direction of the wind. You can see on the figure, top right hand, the flapwise bending moment. And then when we add this edgewise bending moment and the flapwise bending moment, it gives us the rotor thrust. That is like the force that acts on the rotor on the wind turbine. So the forces are acting at the distance, which generates movement. So this moment is the moment that we call the torque on the rotor. There's also the tower base moment, which is the fore aft and the side to side. So as a result of the forces that we have at the tower top, it generates a moment at the base of the wind turbine, one in the direction of the wind, and the second one that goes in a perpendicular direction, basically side to side in a plane. You have in the X1 and X2 directions. Those are the tower base, fore aft, and the side to side moments. Also, there is the yaw bearing loads, which is the flapwise, edgewise bending moment added with the sulfate of the nacelle at the top of the wind turbine. And then there is the drive with the torsional loads. Torsional loads also act at the tower top that has resulted in the rotation there. So these are the loads that act and they affect the operation of the wind turbine. Some of the forces of the load can get up to a magnitude of 5 meganewton, and the moment can get up to 5 meganewton meter. So these are huge loads that affect the operational capacity of the wind turbines. So the first load emulator that we did was basically get these loads and find ways that we can actually predict these loads and carry out fatigue analysis based on these loads. Can we go to the next slide, please? So what we had is, we had these loads from Siemens. On the top here, you can see the data set that we had. So we had two sets of data. We had a simulation data set and we have like a measurement data set. So simulation data set were from a real live wind turbine. They were essentially from Siemens that they use for the simulation processes. And the measurement data sets, those are the data that we got from an operational wind turbine. So what we did was, firstly, we used the simulation data to train the model, and then we verify that on the measurement data sets. So for the simulation data, this is like a placeholder. This is not the real values because obviously we don't share the data, as Siemens wouldn't allow that. So these are the normalized data sets that we had. This is just like an indicative of how the data looks like. We had almost 40,000 sample points of the data for the loads, which included the tower top, that is the flapwise, the edgewise bending, the load on the tower top, and then the bending moment at the tower base, both in the X and Y directions. And then we had the measurement data sets in a 10 minutes data interval. And also for the environmental data, we use the open source meteorological data. So it's basically any wind forecasting websites or any meteorological website that they have open data sets. You can easily go there and plug in the location of the wind turbine and generate the wind speed, air temperature, humidity based on that location of the wind turbine. Those were the environmental data that we used. And then the rest are based on the on the wind turbine from the simulations. So how those data were obtained? Basically, they have sensors on the machine, on the wind turbine, and those sensors are what produce this data. So part of the importance of this project is that instead of having those sensors, we can train models based on data that we've already obtained previously, and then it can reduce cost of operation of the wind turbine because we have already obtained a huge amount of data on various conditions and various operational capacities. So this will reduce the cost of operation by eliminating the need of those sensors. So firstly, what we did when we got the data, we had to analyze the data, look at the distribution. One of the distribution was we did the histogram. So the histogram, we had to look at how was the distribution of the data. So the first of the distribution that we had, like the wind speed, we had almost like a uniform wind speed, and then same goes for the shear coefficient. But when you look at the tower bottom X, that is the fore aft, and the tower bottom Y, which is the side to side, and they have a skewed data distribution basically, which is they have a negative skewed, which means they are more likely to occur on the lower values. And then it shows us the distribution of data, the outliers, the symmetry, and the majority of the distribution. So this is like the information that we generated, we got from analyzing the first sets of data set. Moving to the next slide. So we did a density plot as well to look at the concentration, the modalities, to see the peaks, and gives us an excellent indication of which data points appeared the most, to give us a general idea of how the data set looks like and how the distributions are. Those are the first univariate analysis of data that we did on the simulation data set at first. Moving on. So the next one we did was like a multivariate analysis of data. For this one, we tried to look at the correlation between two sample points. So we created the Pearman correlation matrix and the Spearman correlation matrix. And we tried to look at what kind of correlation there exists between all the sample points we are trying to look at. The loads and the loads, the environmental conditions, the power generated, and the rotor speed, the Nusselt acceleration, we plot against each other. So why we use these two different correlation metrics are based on the distribution of data. Some of the data are not normally distributed, and then some of them are skewed. And this different Pearson correlation metrics and Spearman correlation metrics gives different kinds of information. So for example, for the Pearson correlation metrics, it measures linear relationship between continuous variables. But some of the relationships that we have between data might not assume to be linear, might be nonlinear. And then it also assumes that data are normally distributed. But the data that we had from the initial histogram and univariate analysis we did of the data shows that not all the data is uniformly distributed, and also sensitive to outliers. From the univariate distribution, we saw that we had some data that had significant outliers, and it has range between -1 and +1, -1 being negatively correlated, and 0 being no linear correlation, and +1 being there is a perfect positive correlation. So why the Spearman correlation coefficient was a little better than this was because it does not only give a linear relationship between the data, also have monotonic relations, and it does not assume the data to be normally distributed, which means part of the data that we had were not normally distributed. So this is a very good measure to look at the correlations between the data, and it's less sensitive to outliers. Also have the same range from -1 to +1. -1 meaning it has perfectly negative correlations, and +1 meaning it has perfectly positive correlations between it. It's better for ordinal data when the relationship between the data is not strictly linear. So that's why Spearman correlation metrics became like a more indicative of our need here for our data sets. So moving to the next slide. So on this slide, we looked more not only on two variables, dependencies of the data sets on two variables, we look at three more the relationship between three variables. So we look at the power output against the wind speed and the turbulence intensity. So on the left here is the plot that we had for the simulation data sets, and it matches perfectly with what we have the theoretical power curve of a wind turbine. So it has stages on it. It has the cut-in speed. The cut-in speed is the speed at which the wind turbine starts producing energy. So below this speed, the wind turbine generally doesn't produce any energy. And then it produces energy linearly until it reaches to its rated power. So the rated power is like the maximum energy it can produce. So once it gets to the rated power, increase in wind speed doesn't necessarily generate more energy on it until when the wind speed increases to a certain amount, which you call the cut-in speed. Essentially, the wind turbine shuts down because it reaches a point where theoretically, it can't handle the amount of wind without damaging the actual wind turbine. So there are typical values for it. These are like the theoretical values that they have. So for the cut-in speed, around 3 to 4 meters per second, that's when it starts producing energy. The rated power, usually the wind speed is around 12 to 15 meters per second. And then for the rated speed for the cut-in speed of around 25 meters per second. So as soon as the wind gets greater than 25 meters per second, theoretically, it stops producing power. Notwithstanding, there are wind turbines bigger ones and stronger ones that can work in more severe conditions. So this was the plot that produces what we were matching at, what we were looking at theoretically. And it shows how the turbulence intensity interacts with the power curve. So moving on. We go on to the first one, the first load emulator that we did. So the general idea that we had was first get the data set, look at the data set, see if we have any outliers, if we need any cleaning or look at the data structure basically. And then we fit in models. We fit in both linear and nonlinear models after doing the data exploration that we just did. And then we look at the models that we have, we evaluate, and then we analyze the bias of the model based on environmental conditions. And then we come up with pre-trained load emulators, which basically can have values that we would use in the same schema that we have and can predict the loads on the wind turbine. So this is the general scheme of the whole thing that we had. Moving to the next slide. So from the data set, the values that we used for the input variables, which are the independent variables, first we use the power, the electrical power. So the power indicates how much energy the wind turbine is generating, which corresponds to the whole loading system of the wind turbine. And then we have the velocity of the azimuth, which is the rotation of the rotor directly affects the dynamic loads on the components. And then we had the pitch angle, both in X and in Y directions. So the blade pitch also influences the aerodynamic loads on the blade and the entire wind turbine system. And then we have the nacelle acceleration also, which will also fit in as an independent variable. So the nacelle measures and captures the dynamic motion of the nacelle, which can indicate an overall structural loading and vibration. So the loads that we were trying to predict, the first one, as explained before, the blade flap bending moment, which represents the out-of-plane bending of the blade, and it's perpendicular to the rotor plane. So we had also the blade edge bending moment, which refers to the in-plane bending of the blade, which is parallel to the plane of the rotor rotation. We had the tower bottom fore-aft bending moment, which was the rotation, the bending moment at the base is the bending moment experienced at the base of the tower is in the wind direction. And then we have the tower bottom, which was side to side. And then this is the bending moment at the tower base perpendicular to the direction of the wind. So at the top also we had the fore-aft and the side-to-side movement, and then we also had torsion, because the torsion of the drive of the nacelle at the top of the wind turbine that is generated as a result of force applied at a certain distance. So these are the two variables that we had. We had the inputs as our x, and then our target variables as our y, which are the aerodynamic loads that we're trying to predict. So this gives us a simple regression model that we have to train. Based on the data sets that we had our inputs and we had our outputs on the simulation data sets. So it was simply a matter of fitting models to see which is the best to predict the data that we had. So the initial idea was to use as many regression models as we can possibly have. We started from like simple linear regression models, and then to more like complex non-linear models. And then we try to train those various models and have a rating of them and see which models are more indicative of the actual result that was going on. It became apparent that like the linear models were nowhere as close as accurate as the non-linear models. So the initial thing that we did, we just discarded the linear models and we went on with non-linear models to train the data set with. So this is the variable assignment. This is how we did. We use Python and Python, Google Colab. So we fit in the variables, y as the blade flap, which is the load flap wise, and then blade edge, which is the edgewise bending, the tower bottom x, that is the fore-aft, and then we have the tower bottom y, which is the side to side. The same applies for the top of the tower. We have the tower top in x is the fore-aft, and then the tower top in the y, which is the side to side, and then we have torsion at the top of the tower. Then we had the x. So the x variables that we have the power, the velocity azimuth, the pitch angle, and then we have the nacelle acceleration. So all these values we had, not only do we have the exact values at the 10-minute mark, but also we had like, because they are over a 10-minute interval, so we had like standard deviation of the values. We had the minimum and the maximum. We decided to use all of them. I mean, if we had like a feature engineering, we could easily delete some of them, but we just decided to keep all of them and use them. So we fit them in X and Y. So we used the model training. This is how we did it. After discarding of the linear models, which were nowhere as accurate, it became apparent they were nowhere as accurate as the non-linear models. So we had models like random forest, gradient boosting, because it is a multiple output. So we imported multi-output regressor model, XGBoost, LGMB, and then we fit and train this model using just a random state and starting an estimator. So this was the first initial model that we had. This was the second trial. We had a couple of iterations, but this is when it started making sense. So that's why we started from here. So we go to the next one. So at this one, this is what we got. So after training this model, so we look at all the various load channels, which were the loads that we're trying to predict, and look at what models were best when it came to estimating it, determine in terms of like training and testing data set that we had the splits and then the validation data set. So we look at all of them, and what we saw that is like different load channels were predicted by more accurately by different models, if you were. So the metric that we use for measurement, I mean, we tried different metrics, but it was difficult to have a standard metric which represents different, because they had different scales. So what we decided to go with was the mean absolute percentage error, which is basically is a percentage error of the actual value. So it gives a more indicative result because they have different scales. So initially what we saw is like overall the random forest model was like the best when it came to predicting the results. It predicted it the most. But then when we went further and look at individual cases, individual load channels on the wind turbine, like on the next slide. Yeah, what we had was the blade flap the blade flap, the tower bottom X, which is the fore aft, the tower top X, which is the fore aft at the top, the tower top Y, which is the side to side at the tower top Y, tower bottom Y, side to side at tower bottom at the tower bottom. They were all very accurately predicted, more accurately predicted by random forest than the rest of it. But when we looked at the edgewise bending moment and the torsion, the XGB was a more accurate model to predict them. So what we decided to do was to have like an ensemble model of the models that we had, or the random forest is already an ensemble model, but we created this set of model that it composed of multiple models, the random forest and the XGB, where we fit in some of the load channels that were more accurately predicted with random forest, and those that were more accurately predicted with XGB. So here on the left, we saw the random forest was the more, in terms of the bias variance trade-off, was the most accurate. But then when it comes to other models, intrinsically all of them, it was a bit different. So what we decided to do was to have this composite model, or an ensemble model, if you will, that encompasses of these two models indeed. When we go to the next slide. Yeah. So because when we started, we just started with a random state and a random number of estimators. We had to optimize the model. So we had, I think, 7 load channels to predict, which makes for a lot of possibilities when it comes to like using hyperparameters that we could tune. So we could tune the number of estimators, learning rate, maximum number of depth, which would have taken so much time, a lot of time and resources. So we basically narrowed down to 2 most important ones that we felt that were most important when it comes to random forest, which is like the number of estimators and the maximum depth of the 3. And we use grid search to have an array, to look at an array of values for the estimators and the number of 3s, and come up with the most accurate, or how to make the model to be more accurate than it was already. So we defined the parameter range on grid search. We created grid search of all the combinations, which is like partly of the diagram you see on the left. And then we train, and optimally, we choose the best model with the best hyperparameters that were tuned. So this is what we're trying to explain on this slide here. So moving on to the next one. So at the end of it all, what we came up with, this is the most accurate model that we could come up, the most accurate regression model that we could come up with when it came to predicting this load, the load emulator. So we had the number of estimators, the maximum depth, and the learning rate. The learning rates didn't have much to do with the random forest. It was more for the XGBoost. The optimization of the learning rate of the XGBoost kept more accurate, didn't affect the random forest as much. But this was like the best like visual form that we could come up with for the first load emulator. So this was the model that we had at the end of the whole training of the data. And then this was the best and optimal model that we could come up with that gave the best results when it comes to the simulation data sets. So the next one, we then look at the model bias analysis. So why we wanted to do this was to look at how does the model apply under the different environmental conditions. And then when we looked at the environmental conditions and tried to figure out what was the most important one, instead of having like multiple environmental conditions that we could look at, we looked at the turbulence intensity, air humidity, temperature, the wind speed. So it became apparent like the wind speed was the most important bit. So we used the wind speed for the model bias analysis. So we tried to look at different wind speeds and plot against our performance, like our predictions, and see whether the model is biased towards lower wind speeds or whether it was more accurate towards mid-range wind speeds or to a higher wind speed. But in all, the loads, the accuracy became quite uniform throughout the various wind speeds. This is the plots that we have here. And the lower wind speed, the higher wind speed became, the model didn't have any bias towards specific range of wind speeds. It was pretty accurate uniformly. So we were happy with this model. It meant that we didn't have to go back and try to tweak it over and over again. And we were happy with the model that we had. So this is the end of the first model that we developed for the load emulator. So the next one that we did was for the power forecasting. So for the power forecasting model, it was in a similar vein that we did with the first one. The structure was basically similar. We had the environmental condition, which is the meteorological data that we had, open source meteorological data. Within a time range, we had to do some data matching and time matching to match the same data sets with the power that we had from the simulation data set from Siemens to make sure we have the same date and the same time, the same location, longitude and latitude. We have to reference the same data, download the CSV data, reference it, cross-reference it, and have the same time interval. And then after doing that, we went on to explore the data as well. Data exploration, look at the histogram, plot density, and we looked at the multivariate data analysis, and then we looked at the 3D plots, and we had to do all of that for the data preparation, and then we moved on with the regression model analysis. So what we did fit in the model, we fit in linear models. At this time, it was pretty accurate, like pretty apparent to us that linear models were not the best representation for this kind of models. So we already discarded linear models. We were going with the non-linear models, and then we fit in the non-linear models and we evaluated the model afterwards. At the end of the day, the result was a pre-trained power forecasting model that we could use based on environmental data set to predict the data, hourly data, weekly data, monthly data, and seasonal data set. For as long as the Excel sheets can take, we can predict accurately the data. So moving on to the process. So this was the fitting of the data sets. So data variable here we used were the wind speed, air density, and wind direction. And then for the Y, which was the output variable, we use pretty much is the value, the mean and the max and the standard deviation. They're all in the same thing. With feature engineering, you can just remove all of them and just leave the power, the value of the power. So in the same vein that we did the load emulator, we train at this stage the random forest, gradient boosting, and XGBoost based on their random states, learner rate, and maximum depth. We trained these models on the environmental dataset, which was a single output in this case, which meant that the process was a lot faster because a lot less. It wasn't a multi-output variable regression model. It was a lot faster to predict. So moving on to the next one. Yeah. So we looked at the accuracy of the model. So on this one, because we had just one output variable, which was the power. So that means we could, whatever metric we used would basically give us the same result, which tells us the same thing. So we only went with the mean absolute error. And the error showed that the random forest, similarly in the case of the load emulator, had the least amount of error. And then though when it came to training time, XGBoost didn't take any time because it was basically very wrong. And then the random forest, although it took a lot of time to process, but it was still the most accurate that we could get. So after looking at this, evaluating this result, so what we had to do next, we had to optimize the model. We had an accuracy, but we wanted to improve the accuracy. So on the next slide. Yeah, so this is the results that we got based on the training time, the mean squared error, and the absolute error. So they were basically telling us the same for the mean absolute error and the mean squared error. They would tell the same thing, but the training time was a bit different. So moving to the next one. Yeah, so the next thing that we had to do was we had to optimize the model. Although we had an accuracy, so we needed to tweak the hyperparameters of the model, the number of estimators, the maximum depth also. So we had to choose a range of values for the number of estimators, and then the maximum depth as well. And over a grid search, we carried out a various grid search to look at which was more accurate and find out what was the most accurate model that we could use in all. So the one indicated in red, generated the most optimal model that we had. Moving on the next slide. Yeah, on this slide, we could see the performances of the model on simulation data and the environmental data. So after we done it on the simulation data sets, we also had to carry out, we had a pre-trained model and we wanted to validate it on the measurement data sets. So what this basically shows us was, based on the simulation data and environmental data sets, what was the comparison. It was a pretty good result that we got. So on the next slide. So this, we talk about the results. So here it talks about what we're going to talk about here is the performance of the model. Remember initially I told you we had two data sets. We had simulation data sets, which were from simulation wind turbines, and then we had measurement data sets. The measurement data sets were from a real operational data. And then after training the model and evaluating it on simulation data set, so we had to evaluate its performance on the measurement data set, which were the real operation data sets. So what we found out was when we deployed the model on measurement data sets, because we had an ensemble model when it came to the load emulator for the various load channels, load components. So there was a fluctuation, a difference for every single load channels when it came to predicting it accurately. So this is more like the mean absolute error minus 100 minus mean absolute error to have like a very good visualization. This is not like, mostly the accuracy is like 1 minus the value of the mean absolute error to have like an indicative. This just shows the error of not actually the accuracy, but the error, the mean absolute error that we had, to have like a very good representation of how it is. So the model overall, we said we had like accuracy of like 89% when we took the average over the whole load channel, but each of the load channels had its own different amount of error. But overall, most of the errors was about 10%, which indicated a very good results on the measurement data set. So this was the performance of the load emulator on the on-sim data set, which was the measurement data set from the operational wind turbine. And the similar vein, we went ahead and used it on the measurement data sets for the second model, which we had a second model. Can you go to the next slide, please? Yeah. So this was the mean absolute error of the pre-trained power forecasting model that we had on the measurement data sets. So when we deployed this data set on the measurement data set, this is what we had. We had a mean absolute error of just 3%, which was very good in terms of when error is concerned on on-sim data sets. So this was the result of the deploying on the measurement data sets. So moving on. Yeah, so after doing all of this, we had to deploy these models that we have trained and we have pre-trained and we have stored. So what we used was Streamlit. So using Streamlit, we created a dashboard that would be basically a graphic user interface that is very easy to use, user-friendly, that we had what it does is that it takes, at this point, what it does is like it takes the CSV data that is in a similar sense to when the schema is the same as the one we use for the training. Essentially, if the schema is the same as the one that was given to us by the CSV file is in the same format as the one that was given to us by Siemens. So if you have any data sets on there, you can use it to make predictions on the load channels. Having made these predictions, it can give you information on the fatigue and utilizations of the various load channels. So this is what it does. So on the top right, you upload the data sets. When there is no power utilization, it predicts and tells you what is the utilization of the components of the load or the various load channels. And then it gives you a chance to an aggressive methodology, which allows you to optimize the performance. Instead of just stopping at that, it shows you like the usage of the utility can be increased using 10%, 20% of what is the actual capacity. And it shows you, it gives you an indicative result of how the utilization would be. Would it be safe to increase the utilization? Would it be unsafe? So if it was about, say about 70, 80%, was it safe? And you can also increase it to increase the power output, and you can increase, basically what it means, like from the power curve, instead when it comes to the cutout speed, instead of the wind turbine basically stopping there, it can also shows you can go beyond there, and what will happen to the wind turbine? Will it still be, what will be the utilization? Would it be in a danger zone? Would it be safe? So those are the power boost methodologies. So we have implemented 2 power boost methodologies that talks about the fatigue. The first one is allows you to increase the utilization. The second one even further, and then it compares the efficiency of the wind turbine by using whether you don't have any aggressive methodology, or whether you use the first one or whether you use the second one. So this is the graphic interface. Essentially, which what this does is like it avoids all the back-end programming that we had to do. Anybody could use this. So on the next slide is the second page of the GIU for the first load emulator. So it shows you a comparison of the various how is the power output when it compares to aggressive methodology or no aggressive methodology, or you use the first one or you don't use the first one at all, and it shows you the efficiency between the power boost 1 and the power boost 2 or no power boost. So this first one was the first load emulator. This was the one that talks about this graphic user interface is for the load emulation. And then we have the second GUI, which was the graphic user interface for the power forecasting. On the next slide. Yeah, so this was the one on the next slide. So this is what we have is like based on the environmental data sets, which is the air density, wind speed, and humidity. When we have a schema that is similar to the one we use to train the model, you can implement that. And then it gives you the power output. One of the charts there gives you the power output, the wind directions, and it tells you, it shows you the power output and power projections for months, for a daily output, or like for a seasonal output, based on the amount of data is available. So this was the final products that we had. So the 2 were user friendly and everybody could use them. This was like the end of so this makes like the end of the whole project that we had. So this was our team. Myself, Edmo, Matteo, and then Sammy. Sorry, Sammy, we didn't have any headshots of Sammy.
That's fine.
It's your picture.
Okay, so this brings to the end of our presentation. Thank you very much for listening.
Thank you. Sorry, Sammy, for the picture.
No, it's okay. It's okay. It's funny.
Okay, thanks. For the last time today, any questions from the jury? Most question. Yeah. Who did what? That's I was about to say the same thing. Because to be honest, we heard a lot about the technical part in the introduction. So can you explain who did what?
It was more of a teamwork exercise. However,
Now, can you move in the center?
Thank you very much for the question. What I can say, it was a teamwork exercise, despite the fact that because of resources on Abbas' side, he was more resourceful in terms of providing guidance, and also some as our mentor. But I would say it was more of a teamwork. Where we wanted to do something online, we would set up a session and do an online session for us to come up with this piece of work.
What about, I mean, about the technical coding and Excel? Who did what? For the coding of the...
I would say...
Yes.
About, you can answer if you want, yes?
Yeah, so basically I did a lot of the coding because like I've got a bit of experience doing that. So it was very easy for me to do that. Because for more general maybe inquiries and general structures, maybe non-technical bit, so Edmo, he also did that. He also contributed when it came to that bit because it was a lot of technical things when it came to the whole project. Yeah.
You want to add a comment? Or you...
I think it's
okay. Okay. Thomas, Alex.
Well, just from the point of view of a viewer, it has happened in previous presentations, but it would be nice if you think about the scale that you're using in some of the graphs.
Oh,
because
yeah.
they were hardly visible sometimes.
For the presentation, yeah.
Yeah, so it's, if you're gonna try to sell a product, there is no way you're gonna sell it if you cannot see what is in the scale. Otherwise, we are seeing just a drawing, and we cannot understand that. And also,
yeah,
about would you mind switching to one of the previous? There, no, in that one, in the bottom left, the power output over time.
Yeah,
that's a predicted one, if I'm not wrong. But I'm quite amazed that it has reached the top of it, on the bottom of it all the time, all those days.
Oh, right. So the thing is, when you look at it, right, like you say, just the scaling, like it's just like the scaling, we could have done better because that is like about maybe 3 months trying to compress it in one bit. So it's just about the scale of the diagrams. What we tried to do was to normalize the scale because the data that we had from Siemens was confidential data. Obviously, we couldn't display the accurate data on this chart. So we tried to have a normalized scale of the data. But then on this one, we could definitely do better on this top bottom left, because I think it is, a better graph would be, because it's compressed so many days. When you look at it, it's like November then to January, that is like 3 months altogether trying to compress and plot it over the days. I think a better graph would be a more accurate representation than this kind of graph. Yeah.
I mean, I'm not expert on this at all, but I'm amazed that so many times it has reached the top of the. I mean, the bottom I can understand it, but the top of 6
megawatts.
No, I don't mean I'm not worried about the value.
Okay.
But I'm worried about that. It seems to have reached the top of energy that you can get
from the wind turbine.
From the wind turbine so many times throughout the year, when you also crossing on. I mean, you got May, on July.
6 months, yes.
Yeah, so
it's like winter.
In Spain we got a lot of wind turbines, and they are usually top of energy on winter, but not in spring or summer. So I don't know. I'm just guessing. I'm not an expert on this, but if you're showing some data, they should be accurate.
Yeah, what I can say is that I think since we just presented it as a dashboard, it was going to be much more clear if we had just taken that parameter and presented it on one slide.
Sami, if you want to add any comments.
Yeah, just the data that I provided to them is the same data set for both projects. And we have a constraint on the first project for the load emulator because we wanted to discard some complexity induced to, for example, storm on the really rare event that can cause extreme loads. So I filtered the measurement data just to collect normal operation case. So on this, it has been used also for this second project. So this is why you often see that the turbine is reaching almost its maximum capacity because you almost have data under normal operation. Like we didn't take the whole data set for a specific, the whole data for a specific time frame, and then we applied this model. Yeah, it was just for visualization, but yeah, in reality, the values are much lower than what is shown here.
Okay, thanks a lot. Yeah, thanks for the compliment.
Yeah.
It's theoretical data.
And yeah, sorry if most of the plots were not that intuitive due to the fact that they had to normalize the data, but it's because ABBA and Edmore have signed a confidentiality NDA. And yeah, on one term of this confidentiality contract is to not share not normalized data. So yeah, sorry for that, but it was a constraint that they needed to respect.
I just was wondering, I mean, it didn't.
Now it's clear. It's clear now.
It is so clear.
Now it is clear with your comment. Perfect.
Yeah.
If you have any question you want to ask, Sami, feel free.
Well, I already went to the presentation, so I already made some comments. Yeah, the only comment I would have made when you were showing all this data exploration, yeah, I just have a, well, I just wanted to precise that this data exploration part was really useful, especially when you are showing this correlation matrix. What is important is not only to check if some features are correlated between them, but it's also important to check which feature is completely uncorrelated from the other, because it might mean that this feature has really crucial information which is not encoded by the other information. And we can see on the correlation matrix that ABBA has displayed that we have some features which cannot be reconstructed at all. And some environmental conditions cannot be reconstructed at all. So this is why we spent a lot of time on data exploration, because understanding that will permit to see if for machine learning model have some bias or not. But yeah, for example, the air density, which is an environmental conditions. So I don't know if it was clear, this explanation, but for our load emulator, we are using SCADA data from the fleet, but we also have environmental conditions so the environmental conditions are wind speed, air density, wind profile. We also have this information, but we cannot use it because we assume that in reality, we do not have access to this information. So what was important for ABBA and Enmore, and that was taking a lot of time, and this is why we spent time on data exploration, is to understand all the complexity, all the correlation, the relationship between all the features, to understand what can be reconstructed and what cannot be, to understand if our model will have some bias. So yeah, this is something that perhaps was not clear. So yeah, I just wanted to explain that a bit further. But I don't know if I have confused you more than before. So, but yeah, I just wanted to make a remark in general is that this project was quite complex because first I'm a machine learning engineer. So this project was more focused on building machine learning models. So I know you had some lectures on machine learning, but I mean, you are not expert on that. And yeah, I had quite high expectation regarding this part. So yeah, you have the students made a lot of effort digging into machine learning concepts and also the important thing is yeah, the wind turbine field, especially our field. It's an R&D project, an industrial R&D project, so it requires a lot of domain knowledge concepts. For example, one thing is this cut-in wind speed, cut-out wind speed, but it's only one concept among really a really non-exhaustive list of concepts, and they managed to yeah, to understand this concept, to play with the data, and because if they were not understanding this concept, they would have not managed to build this machine learning model successfully. So well done, Abba and more for this point.
Okay, thank you, Sami. I think we had a last question from Jeremy.
Yeah, I have a few questions.
A few.
I was just wondering about the data that you had. Is it a time series for a few wind turbine, or is it just a fixed average value of wind speed or stuff like that that I didn't get? It's
Okay. Yeah.
Yeah, go on.
Yeah, so the data we had from the simulation data sets, we had 10 minutes interval of data. Not only on the 10 minutes, we also have values on, you see the values that we have, the maximum value, the minimum value, the standard deviation. When you look at some of the values there, you see that. So it's a time series data over 10 minutes interval for the simulation data set. I think same thing with the measurement data set also over 10 minutes. And then when we went to collect the data for the meteorological data, we also had to take, I think it was over 20 minutes but it wasn't the same time scale when you look, because they were from two different sources. This was from Siemens and that one from environmental data basically. And then you had to like match it to match accordingly, like to convert the time scale, so that we can have essentially similar time scales. I don't know if that answers the question, but like in terms of like when it comes to the time series of the data, yeah, that is how it was.
So when you speak about min and max values, is it on the 10-minute time scale, this min and max? Or
Yes, on the 10 minutes time scale, yeah.
So what you predict actually is the force, some kind of average force over this 10-minute interval.
10 minutes intervals, yes.
Okay. That wasn't clear for me. This brings me to my next question about how do you do fatigue analysis based on the output of the model? Because you said this is useful to do fatigue analysis, but you didn't really explain how you would use the results of your model to do fatigue prediction.
All right. So what we had is usually the wind turbines, they have like a fatigue limit because it's a cyclic load that is applied to them, like maybe the flap edge bending and then the flap wise and the edge wise bending. All the loads are cyclic in nature. And then what we had, like we sum up these loads over a certain period, or it goes out over billions of cycles. And then the time the wind turbine manufacturer generally have like a fatigue limit. So this is the maximum number of cycles that a wind turbine can have. So we can predict the number of cycles of these loads that we have, and then with the limits that is given, and then based on that we can say we can subtract, like, okay, this is the fatigue, and this is the remaining life on the wind turbine based on this particular fatigue channel. Yeah. So basically it can go over more cycles, or if it can go more above the limits that it has already gone. So this was like kind of the idea that we had for the aggressive power methodology, power boosting methodology.
So it's Siemens that provide you with a fatigue criterion based on the loads, external loads that are applied on the wind turbine, right?
Yeah, basically all the wind turbines, they have their limits.
Okay. So because here you have a fluid structure interaction problem. So basically your machine learning model is trying to predict the fluid parts. You have environmental conditions, wind speed, etc., wind orientation, and you predict the load that is acting on the wind turbine, the external loads, but you are not really solving the mechanical problem of how the blades they deform, because you also mentioned crack detection, etc. So I think this is a bit overstatement to say that you will be able to perform crack detection just based on macroscopic load resultant at the base of the wind turbine or something like that. So you will need some additional layer, maybe using machine learning or simulation to predict the behavior of the pylon and the blades, and to do accurate fatigue prediction on this scale. So that was not.
They are counting cycles.
It is just
different stresses, but counting cycles.
Yeah, sure. But so it's basic fatigue
Okay, thank you. Thanks.
Problem.
Anyone for last question? Yep, no, it's fine. But thank you again. Bye. And thank you again, Sami, for being here and to have acted as a supervisor.
Yeah, you're welcome. Thank you for this opportunity, Mathieu.
You keep in touch, as we say. And,
yeah, of course.
Thank you.
Yeah, have a good evening, everyone.
Bye. With this last capstone ending, I think so the day is finished for today. Thanks again for attending. We will meet tomorrow morning at École des Ponts. So remember to follow Disneyland sign, but stop at Noisy-Champs. Okay. Keep the badge, please. If you think you're going to lose it, you give it to Geraldine. She will be the badge keeper. And so for tomorrow, please, have you seen we were way behind schedule. And for today it was okay, but tomorrow we are very tight, specifically at lunch. So we will start the first one from IESA at 9 a.m. sharp. So please be here at 8:30. I know it's early, but the day will be long, but we will have breakfast, coffee, and etc. And we will start very like sharp. Yeah, sorry. Yeah, so last minute change. Obviously, we have a problem in the auditorium. Obviously, so we had to change the auditorium. So it will be in the big called Cauchy, like the Cauchy stress and mechanical. So there will be a lot of science inside the school. You follow the science, but if you forget, it's Cauchy.
Like the mathematician.
Like the
yeah.
Like he was a teacher at École des Ponts.
Oh, nice.
Thanks again. Thanks to all the people who were connected remotely. Thank you, Abba, again.
Thank you, Mathieu. Thank you.
And so tomorrow we will have a new session on Zoom. And it's the afternoon, another one for the graduation ceremony. So stay tuned if you want to follow for tomorrow.